In this video, we're going to discuss a little bit about Cisco certifications. So let's start off talking about this course that you're about to embark on. This course is for the ICND1 exam, or Cisco exam 640-822. Now, if you take this exam and you pass this exam, this will get you the certification of the Cisco Certified Entry Networking Technician, or the CCENT, which is a relatively new certification. It's come out in the last few years. And it's to validate that you have a very basic level of understanding about Cisco networking equipment, the basic understanding about routers and switches, the iOS, and the various hardware platforms that make up a Cisco network. The CCENT exam, or the ICND1 exam, is also one of two recommended courses for the CCNA, or the Cisco Certified Network Associate. The other exam that you would have to take for the CCNA is the ICND2 exam, or exam 640-816. There is, of course, a training course for each of these exams, and obviously you're on the ICND1. And if you were to continue down the routing and switching course, like 90% of engineers do, then you would take the ICND2 course and exam. Now, if you don't want to take two exams, and you just want to take the two courses and don't want to have to sit through two exams, Cisco does have an option to take one combined exam for the CCNA, and this is the route that I picked when I got my CCNA. It's exam 640-802. Now, some people might think, well, if it's one combined exam, I'll just pay for one exam instead of the two individual ICND1 or ICND2 exams. Unfortunately, Cisco's kind of got you there. The 640-802 combined exam costs twice as much as either of the ICND1 or ICND2 exams, so you're going to be paying the same either way. It's just you'll only have one exam to sit through, and if you're like me, the fewer tests the better, because I don't really do all that well with tests. It's something to do with the way my mind is laid out or something, I'm not really sure. And so now that we've mentioned the CCNA, now's a good time as any to bring up the point that there are different specializations for the various CCNA certifications. And there are those certifications: routing and switching, which is the CCNA, ICND1 and ICND2. You have the CCDA, which is the design exam, which validates that you know the basics of designing a Cisco network in Cisco-approved manner, I should say. You also have the CCNA security, service provider, storage networking, voice, and wireless. They're all pretty self-explanatory. If you want to see the different exams for the CCNA specialization tracks for anything besides routing and switching, you can go out to Cisco's website and look in their certification section, and you'll see all of the different exams you have to take for CCNA service provider and CCNA voice and CCNA wireless, for example. The one thing that all of these specialized CCNA certifications have in common is that they all require the CCENT as the first stepping stone. So this course will prepare you to get any of the CCNA specialized certifications, whether you're going for just the straight route and switch, or let's say you're a voice engineer, if you wanted to get your CCNA voice and then move up to your CCNP voice, you can get there from the course you're currently taking. And of course, each of these certification tracks have their own specialized exam requirements. And again, you go out to Cisco's site and you can look at those exams. Speaking of the different type of certifications, this is Cisco's networking pyramid that you'll see on their certification page. It lists out all of Cisco's exam levels from entry, which is the course you're taking now, up through the associate, professional, expert, and architect. These certification levels correspond to the CCENT, the CCNA, the CCNP, the CCIE, and the CCA, Cisco's newest certification. That's the Cisco Certified Architect. And the CCA exam is different than all of the other technical exams. The CCA exam is basically like a doctoral thesis. You write up a network plan or a thesis about emerging trends in networking, or how you would architect a particularly vexing implementation. And then you go before a board of other CCAs and you defend that architecture document to them. And if they think you've passed, then you pass. I personally don't know anyone who has a CCA certification. All of the technical people I know stop right here at the CCIE. So this just gives you an example of how far down the rabbit hole you can go when it comes to Cisco certifications. That concludes our discussion of Cisco certifications. This is the course overview video, or as I like to call it, the What Are We Going to Learn Today video. This video is going to list out what we're going to go over the next few hours as you go through this course. Now, as I've mentioned, this course is the IC&D 1 exam prep course, so it follows the track for the CCNA exam. If you were to go buy one of the Cisco Press books for the CCNA exam, the IC&D 1 exam, you would find that we cover all of the topics in the book. Now, some we cover more in depth than they do in the book. Some we don't really go into as much depth as they do in the book, because honestly, a lot of the exam prep books I've seen for this level of certification, a lot of them will start out very basic. This is a computer. This is a network. This is how they work together. This course, we're kind of crunched for time, so we assume that there are certain prerequisites that you already know before you take this course. Basic computer knowledge. You know what a computer is, you know what a mouse is, you know what a network cable is, you know how basic networking works and basic computing works. And above all, you have to have a desire to learn, because that's one thing that will serve you well in your career, whether you do networking or voice or whatever you do. If you're dealing with computing technology, you have to be willing to learn and willing to adapt throughout your entire career. That being said, let's get down to the nitty-gritty of what we're actually going to cover. We'll start off with the network building blocks. We'll talk about the basic terminology of network building blocks. We'll talk about the OSI model and all of its 7 layers and how it works together to make a beautiful 7-layer network cake, as it were. We'll cover the basics of Ethernet. We'll look at the frames and determine how the frames know how to get from one workstation to another and what it does once it gets there. And then we'll talk about switching, the building block of the LAN, and basically how switches work, how they get the data from point A to point B, and then we'll move on to TCP/IP networking. We'll talk about IP address basics, what an IP address is, what each of the octets of the IP address means, the different classes of IP addresses. We'll talk about how switches and IP work together, basically the layer 2 and 3 interaction that the address resolution protocol provides. We'll talk about some fundamental network services that you pretty much have to make any network work properly, DNS and DHCP being those fundamental network services. We'll talk about how they work, how they keep your network running in tip-top shape, and how your life would be ever so empty without them. We'll then move on to network security. This being a very entry-level course, we don't talk a whole lot about network security because that's just not what's covered in the exam. However, we do have to mention it because it is on the exam and because every good network engineer has to take network security as their responsibility. As I'll mention in the course, there are large corporations that do nothing but security, and any large organization may have their own dedicated internal security team. But you as a network engineer have to be security conscious, and so we'll cover the very basics of network security in this course. We'll then move on to switch configuration. We covered the basics of switching a little earlier. In this case, we're actually going to console into a switch and we're going to configure the basic configuration options on the switch. We'll talk about switch and port security, how you can secure ports from being used without your knowledge, how you can secure the switch so that only authorized people can get into the switch and do anything they need to do on the switch. Then we'll move on and talk about wireless LANs. Now again, this being an entry-level CCNA course, we don't talk a whole lot about wireless networks, but we do talk about the basics and about the various standards, and how a wireless LAN can interact and help or hinder your wired LAN, and some of the things that people may not take into consideration when they're putting a wireless network together. We'll pause this course overview here. We'll pick it up in the next video so we're not too crunched for time. So we're carrying on with our course overview. After wireless LANs, we will talk about IP routing, the heart and soul of the CCNA course, in my opinion. We'll talk about router basics and configuration, how to console into a router, how to do basic first-time configuration, and what all the different options mean. We'll discuss routing protocols, the various types of routing protocols, distance vector and link state routing protocols. And then we'll move on to the evils of static routing. I'll show you how static routes work, why on a large network they should be destroyed with fire, in my opinion. And then, of course, I'll explain why I believe that static routes don't really have a place in a large enterprise network, if at all avoidable. We'll then talk about RIP, or the Router Information Protocol. Now, RIP is a very basic routing protocol, and it's supported by nearly every device out there. It's one of the easiest to set up and configure and verify, and so that's why they cover it in the CCNA, just to kind of get your feet wet with routing protocols so you know what's coming as you progress further down the certification trail. We'll then talk about wide area networking. We won't talk a whole lot about the nuts and bolts of how to configure wide area networking other than to talk about the types of WANs and to talk about internet connections. We'll then spend a little time about the various types of point-to-point connections, the encapsulation, and how to configure them. It's very easy to configure a point-to-point connection. And then we'll touch on frame relay, and frame relay can be a little more difficult to configure than point-to-point connections. We won't configure them in this course, but if you follow on with the IC&D2 course, that's where we get more in-depth with frame relay. We configure up a frame relay network and look at the various types of frame relay networks. But again, that's the next course and not this one. We then move on to in-depth Cisco device maintenance. We talk about the Cisco Secure Device Manager. And as I'll point out when we talk about the SDM, as of the time of this video's recording, is about 4 years old, and it takes a special dedication, if you will, to get this SDM working on modern software and hardware. The SDM has actually been superseded, but because it is in the CCNA course, we have to cover it. And so you'll see how it works and how to do basic configurations in the Cisco Secure Device Manager. We'll configure NAT and DHCP using the Secure Device Manager. We'll talk about file system management, how you can manage the files on the router, the flash, and the config. We'll also talk about TFTP and how it can play a role in maintaining your routers and your router configurations, and helping you back up the configurations on your router in case it gets destroyed by a particularly irritated user with a baseball bat. You can put it back exactly as it was before he took a bat to it. We'll then talk about password recovery, because everybody forgets a password now and then. That's why we have password recovery on nearly every website we visit. And we'll also talk about boot management, or how to tell the router what flash file system to boot off of. We'll then move on and talk about CDP, or the Cisco Discovery Protocol. We'll discuss what it is and how it works and how it can help you build a mental map of your network, and how for some types of networking it's pretty much required. We'll then move on to the lab. Everybody loves the lab. In this lab, we will meet Joe and Joe's widgets, and we'll build a network for him. We'll set up DHCP and NAT and static routing and routing protocols and the whole 9 yards. Everything we've covered in the course will be configured in the lab in pretty much real time. Once we're done building the small network, we'll verify that it actually works like we expect it to. We'll break the network and see that the network actually fails in the manner that we expect it to. The case of this small network, it doesn't actually fail. It's pretty robust, but it performs exactly as we'd expect it to, because that's how we've configured it. And that's it. That's the course overview. That's what we're going to learn over the next few hours. Strap in. It's going to be a fun ride. So we're going to start with the basics, and we're going to talk about network topologies in this video. Now, the topology, in a networking sense, is the physical or logical layout of the network. We make this distinction because the physical and logical topologies are not necessarily the same, so you can't always tell what the logical topology is from the physical layout. We'll get into that a little more in depth later in this video. But first, we're going to talk about the 4 common topologies you will see on local networks and wide area networks. They are the bus, ring, star, and mesh topologies, and the mesh is somewhat divided between the full and the partial mesh topologies. Now, each topology has its own advantages and disadvantages, and we'll go into each of these over the next few slides. The first topology we're going to talk about is the bus topology. The bus topology, on a physical level, is where every network device is connected to the same piece of wire. You have a bus that goes from one end of your network to the other, and each of these devices connect to this same physical piece of wire. Now, if we're talking about a physical bus topology, you may remember twin-ax, or you may remember thick Ethernet with vampire taps if you've been around quite a while, although you won't see those in modern networks. However, you will see a logical bus topology if you happen across a token ring network. And again, it's been a long time since I've seen a token ring network personally, but I'm certain they're still out there, and they're far more common than the old thicknet networks. Now again, this is a physical topology that we're looking at. Now you can have a logical bus topology and a physical star topology, and we'll talk about the star topology here in a couple of slides. And honestly, that's what most Ethernet networks are. They are logically a bus because all of the Ethernet computers are connected to the same physical piece of wire. But looking at the physical layer, they are a star because there's a hub or a switch in the middle of your Ethernet network, and all of the devices plug into that hub or switch. So the next topology we'll talk about is the ring topology. Now, I'll be honest, the only place I've ever actually seen a ring topology in use on a physical level is certain point-of-sale systems back in another life almost 20 years ago when I first started getting into technology. And essentially, the impulse goes from one end of the network to the other and just keeps going around and around and around this circle like so. Each device is connected to two other devices. The downside to this ring is if this link here is broken, then your whole network goes down because the traffic really only goes one way. Most ring topologies, at least on a physical level, will have counter-rotating rings, or they'll have dual rings. One ring goes this way, the other ring goes this way. And this way, if one of the rings are broken, the traffic can still go the other direction to get to every node on the network. Again, a ring topology is not really anything you'll see on a physical level, but you will see them on a logical level, especially with metropolitan area networks or certain other wide area networking technologies. The third topology we're going to talk about is the star topology. And I mentioned this a little earlier when we talked about the bus, but the star topology means that every device is connected to a central point. This is the type of network that you'll find most frequently in use. Again, if you have an Ethernet network with switches or hubs in the middle of it, this is how it's going to be laid out. The advantage of this is that every device is separated from every other device by this cable. So if this one cable goes down, you only lose communications to this workstation or printer or server or so on and so forth. The downside to this type of network is if this switch in the middle goes down, everybody's down. Unlike with the ring topology, where you could have a ring going the opposite direction and still have network connectivity. And the last topology type we'll talk about is the mesh topology. Now, this particular image shows a full mesh topology where every node is connected to every other node. So any one of these links could go down and you could still get to any of the other nodes on the network. This node could go down and, well, I can get to this node because I'm directly connected to it. I don't have to go through anyone else to get to this. You generally only see mesh topology networks on wide area networks because you can imagine the cabling requirements that would be needed to have a full mesh topology on a local area network. Every one of your workstations in this simple network with just 6 nodes, every workstation has to have 5 network cards in it and 5 network cables going to each of the other nodes. It just gets to be really unwieldy. I've never seen this on a local area network. And again, it's only for frame relay networks. Now, I've mentioned this is a full mesh network. I don't have a graphic for a partial mesh, but a partial mesh is basically where every node is not connected to every other node. Let's say that this is a satellite office here. Well, it really only needs connectivity back to the corporate, whereas all of these other branches needs full access to everyone else. So this node here may not be fully meshed with all the rest of them. It may only have a connection back to the central office. And that's a partial mesh topology. Now, you remember way back at the beginning where I said you can't necessarily tell the logical layout from the physical layout. Well, let's take a look at that. For example, let's look at a full mesh frame relay network, which logically looks like this. Any node can get to any other node on the network without having to go through any site. You basically have a big frame relay switch here in the middle that's your provider. However, the physical layout of this network is a star topology because each branch or each one of these locations only has one path out to the frame relay network. But you don't necessarily have to go through this point to get there. You have a logical connection between these 2 points inside this full mesh network. And that's the most obvious example of physical and logical topologies being divergent. The longer you work on networking, the more you'll see physical and logical abstraction. And in fact, when we start talking about the OSI model, that physical and logical abstraction becomes even more pronounced at certain layers of the OSI model. And that concludes our discussion of network topologies. In this video, we're going to discuss the OSI model. The OSI model stands for the Open System Interconnection Model. The OSI model is a 7-layer model that describes how network systems communicate with one another. It's basically a roadmap from the IEEE that tells different networking vendors how they can interact with one another using standard terms and standard functionality so that you can get a network card from Dell, for example, and connect it to a Cisco switch, and you know they're all going to work together, and you don't have to have all Cisco hardware from one end to the other just to run your network. The OSI model looks kind of like this. There's 7 layers, and there's a couple of acronyms you can use to remember the different layers of the OSI model, depending on which direction you want to go with this. Going from layer 1, it's please do not throw sausage pizza away. Going the other direction, starting at layer 7, it's all people seem to need data processing. The more creative among you can probably come up with some other acronyms to go along with the OSI model. But if you're going to do any networking, any serious networking at all, you're going to learn this and love this and know it, and you're just going to know it cold. Now, we're not going to get into a whole lot of depth about the OSI model at this level, at the CCENT. If you're truly interested in the OSI model, there's dozens of web pages that go as deep as you want to get into the OSI model. But at this level, we're just going to cover what it is, what the different layers are, how they interact with one another, and that's pretty much about it. So we'll start with a very high-level understanding of how the traffic gets from one end to the other. Basically, the traffic starts up at layer 7 at the application layer. I'll go back a slide here. It starts up here at layer 7, and as it's passed down each of these layers, each layer adds its own headers to identify the data at that layer. Here's a very crude drawing of what a network packet would look like. Up here at level 5 through 7, that's where your protocols reside, your HTTP, DHCP, DNS. When it gets below layer 5, it goes to layer 4, you're talking about TCP. You get TCP headers at this point, so the packet just gets bigger and bigger and bigger the closer you get to the physical layer. Obviously, the physical layer is what we'll cover first, and there's not really any protocols at the physical layer because it's physical. It's wires and cabling and whatnot. And that's a perfect segue to talk about layer 1, the physical layer. Layer 1 controls the physical aspects of data communication across the network, things like cabling, connectors, voltages, the type of media, whether you're using copper or fiber, the type of termination. And the things you'll see at the physical layer are hubs. They're basically Ethernet repeaters. If they see electricity come in on one port, they send it out all of the other ports. Obviously, the other thing you'll see at the physical layer are the network interface cards that go in your PCs and your servers. At this layer, the transmission is all either light if you're using fiber, or it's electrical impulses on copper wire. That's basically all you've got at layer 1. Layer 2 is where things start to get interesting, in my opinion. That's the data link layer. Data link layer controls communication on the same local network. The data link layer also controls access to the physical media through various mechanisms, and we'll get into how that works when we talk more about how Ethernet works elsewhere in this course. The data link layer also performs error correction on transmitted frames. It can tell if a frame is corrupted in transit and will request that frame be sent again at layer 2 before any of the other higher level protocols have to try to reassemble that frame and determine later on up the stack that, oh, this frame is corrupt, resend the whole thing. Layer 2 addresses are physical addresses. These are the addresses that are burned into your network card. It's the MAC address if you've ever looked at the ipconfig output on a workstation. And again, since layer 2 is really only concerned with local area networks, those MAC addresses have to be unique, just like every address has to be unique. The OSI layer 2 data link layer is technically split into 2 sublayers: the LLC layer, the logical link control, and the MAC, or the media access control. Again, we're not going to get into that in this course. All you really have to know is that they exist in order to pass the exam. Switches and bridges operate at layer 2. Remember where we said hubs operate at layer 1 because hubs are just dumb repeaters. I see electricity come in, electricity goes out. Switches and bridges actually look at the MAC addresses, the layer 2 addresses in the Ethernet frames, and they will say, oh, well, I see that your destination is this MAC address, so I'm only going to send that packet out the one port that's connected to that MAC address. The types of protocols you'll see running at layer 2 are 802.3 Ethernet, obviously, HDLC at SDLC, PPP, PPPoE for wide area networking protocols, and your good friend CDP, or the Cisco Discovery Protocol. Now, we'll get into that a little later when we start to use some of the routers and switches in our lab. CDP can be your best friend when you're trying to troubleshoot network connectivity issues. CDP runs at layer 2 and will tell you what's connected on what ports in your router or your switch. We'll pick up with layer 3 in the OSI model in the next video. So we're picking up with our discussion of the OSI model. We're going to pick it up at layer 3. Layer 3 is the network layer. Layer 3 controls communication on different logical networks, and this is where the abstraction between the physical and the logical comes into play. Layer 3 addresses are logical addresses that can be assigned to any type of Layer 2 device that supports the protocol that you're using. Now, for the purposes of this course, we're always going to be talking about TCP/IP. And IP is the Layer 3 portion of that protocol. And so you can probably figure out that the Layer 3 address in a TCP/IP network is the IP address. And obviously, if you've been around computers for any length of time and you've done any type of networking, you understand that an IP address can be assigned to whatever computer you want to assign it to. Again, it has to be unique, but I can take the IP that's on this workstation I'm currently using, for example, and if I wanted to assign it to my laptop, I could turn off this workstation, assign that Layer 3 IP address to my laptop, and it would enjoy the same network access that this workstation does with respect to firewalls and other Layer 3 inspection. Routers are the type of devices that operate at Layer 3. They look at the Layer 3 addresses. They don't care what the Layer 2 address is. They see you're coming from this Layer 3 network, you need to get to that Layer 3 network. I have a route to get there, you need to go out this interface. Not just for the purposes of this course, but in general, IP is the most common Layer 3 protocol you'll find out there. Whether it's IPv4 or IPv6, which we won't really get into IPv6 pretty much at all in this course, both of those are Layer 3 protocols. The type of applications you'll see running at Layer 3 are ICMP, ping, traceroute, RIP, because all of those really only care about getting the data to the remote network. It doesn't have any higher level functions other than can I get any traffic at all to the remote network, like ping. Ping is technically ICMP, just like traceroute is technically ICMP. It's different methods of using ICMP, and again, we won't get into that in this course. But it's an important distinction to draw out that a lot of people think, well, if I can ping the remote host, I must be able to do anything I want to the remote host. All you're guaranteeing with that traceroute or that ping is that you have a Layer 3 connection to the remote host. You could have services on that remote host that might not be responding, but again, I'm getting a little deep and a little further afield than I need to be. Let's move on to Layer 4. Layer 4 is the transport layer. It is responsible for end-to-end connection reliability. It performs this end-to-end connection reliability by breaking the network traffic into segments that can be retransmitted if needed and if the protocol supports it. Layer 4 is also responsible for byte orientation, flow control, and reliability, which we've already mentioned. So your transport layer can actually throttle your connection should you have quality of service or class of service rules in place for network transmission speeds. The type of protocols you'll see at Layer 4 are TCP and UDP. If you've been around NetWare, you'll recognize SPX, which is the Layer 4 component of IPX/SPX, and ATP, which is an Apple file sharing protocol. Moving right along, Layer 5 is the session layer. Layer 5 manages communications between two distinct endpoints, and it is different from Layer 4 protocols. Layer 4 is really concerned with the flow of the data. Layer 5 is concerned with the applications that use the Layer 4 data flows. Layer 4 gets you there. Layer 5 actually transacts business between two computers. If you've ever used any application that does RPC or remote procedure calls, Layer 5 is where RPC lives. Protocols that live at Layer 5 is L2TP, the Layer 2 tunneling protocol used by some VPNs. NetBIOS, again, if you've done any Windows networking at all, you know what NetBIOS is. PAP, which is the PPP authentication protocol. And PPTP, or the point-to-point tunneling protocol, which is another type of VPN connection. Layer 6 is the presentation layer. The presentation layer basically translates between different encoding methods, and the big example that all of the documentation and all of the classes use is translating between ASCII and EBCDIC, which IBM mainframes use EBCDIC, and PCs all use ASCII. The type of protocols you'll see at Layer 6 are AFP, the AppleTalk filing protocol, NCP, which is the NetWare core protocol that actually still exists with the non-IPX version of NetWare, if you're interested in all that, and Telnet, which basically just spits data at a remote host, and Layer 6 is where that translation takes place in the Telnet client. Layer 7 is the application layer. The application layer presents all of this network data that we've broken up into these segments and frames and packets and bytes. It presents it to the application or the end user on the specific endpoint. Protocols that you'll see at layer 7, HTTP, FTP, SMTP, SNMP, these are all the high-level protocols that you're used to dealing with. I make an HTTP request to the remote system, it spits me back a reply. I send an FTP packet to the remote system, it comes back and says, yes, I've received it, or here's your file, depending on which way it's going. You don't really care about how the data gets there, what IP address, so on and so forth. All you're saying is, that remote machine over there, I want it to get this SNMP packet, and it gets it. And that concludes our discussion of the OSI model. Welcome in. In this video, we're going to go over some pretty basic Ethernet concepts. And when I say some pretty basic Ethernet concepts, we're going to talk about the history of Ethernet, where it came from and how it got to be the most widely used networking system in use today, and how Ethernet works at a very basic level. Now again, this is the CCNA course, so if you're looking for a course that can tell you all about how Ethernet works on the wire and how every little bit in the frame works, this really isn't the course for you. There's all kinds of websites and other video courses that you can take where you can learn everything there is to know about layers 1 and 2. This is not part of the CCNA curriculum, and so we won't be covering it in this course. So we'll start off with the history of Ethernet. Ethernet has been around since the middle 1970s, and the middle 1970s, 73 and 74, is when some pretty smart guys at DEC, Intel, and Xerox got together and came up with the protocols that would make up Ethernet. And they published those protocols in a white paper in 1980. And like any good idea, they found improvements to these ideas that could make networking a lot easier, and so in 1982 they released version 2 of these standards, and it became the basis for Ethernet 2. If you open up an Ethernet capture in Wireshark, which we will do elsewhere in the course, and you look at the frame type of a packet, you'll see that it comes across as Ethernet 2, and this is why it's called Ethernet 2. The IEEE took the Ethernet 2 standard and published it as the 802.3 standard, and the IEEE stands for the Institute for Electrical and Electronics Engineers. Now, as I alluded to a little earlier on in this video, Ethernet encompasses both OSI layers 1 and 2. It not only contains standards of how the electrical impulses physically go across the wire, it also has the data link and media access functions built into the protocol. And as we discussed when we talked about the OSI model, when it comes to Ethernet, layer 2 is divided into 2 sublayers. Now the MAC sublayer controls physical access to the wire, and again that's the MAC address. The LLC sublayer indicates what layer 3 protocol is in the Ethernet frame. Now this is a little different between Ethernet and Ethernet 2, and at the very end of this slide deck I have a picture of an Ethernet frame, or the layout of an Ethernet frame, and you'll see the differences between the raw Ethernet and the Ethernet 2 frames. So let's talk about Ethernet cabling. Way back in the dark ages, the very first Ethernet cables were 10-base-5, referred to as thick Ethernet, and I've got a picture of it here. People that I know that have worked with this basically called it a frozen garden hose, because that's about how pliable this particular networking topology was. Basically, your network segment consisted of one long coaxial cable running the length of the building or the length of the floor or between all the computers in an apartment. And it used vampire taps, which is this device you see over here. And what you can't see inside of this is it's got 2 little fangs, if you will, that pierce down into the wire. One pierces into the outer shell, one pierces down to the middle of the coax, as you see right here in this picture. And in addition to being rather unwieldy, you had this one long coax cable that if someone tripped over it, or if someone rolled their chair over it, or if it broke, or anything, you took down the entire network segment just from one little break in the cable. And I've not ever worked on a 10-base-5 Ethernet network, but I have worked on its successor, the 10-base-2 thin Ethernet. And really the only difference is that the coax cable is a little smaller. It still runs from one end of the building to the other, or one end of the department to the other. It's just instead of the vampire taps, you have this little T connector here. And if you were to go behind one of the computers and just unscrew one of these coaxes from the edges of the T here, you'd take down the entire network, especially if it's a small network where the cable goes from one end of the building to the other. You unscrew that and the entire network goes down. You roll your chair over it, the entire network goes down. It's got all of the problems of the thick Ethernet cabling, but it's a little easier to deal with. Again, about the only nice feature between 10-base-2 and 10-base-5 was that it used these T connectors instead of the vampire taps. So then we'll move on to modern day. Modern day is 10/100/1000 base T, depending upon the speed of the network, anything from 10 megabit up to 1 gigabit. And there are ways you can do 10 gigabit over copper in some of the really high-end Cisco switches, but for the purposes of the CCNA, you're just going to assume that the fastest you'll see on a copper wire is gigabit Ethernet. Now, the most common or the most popular media you'll see is the twisted pair type of media, which you see in the picture over here, although obviously you can use fiber optics as well. And of course, we won't get into that in this course, just simply because we're going to assume that everything you'll run into is gigabit Ethernet running over RJ45 twisted pair. We'll pick up our discussion of Ethernet concepts in the next video. So we're picking up with our discussion of Ethernet concepts right after we talk about Ethernet cabling here. So let's move on to how Ethernet puts its frames on the wire. Ethernet uses a protocol or a method of accessing the wire called CSMA-CD. And that's a big long string of alphabet soup there, and it basically stands for Carrier Sense Multiple Access / Collision Detect. So let's break down this phrase into its constituent parts, since that's really the easiest way to go about it. Carrier sense means that Ethernet will detect whether or not a cable is plugged in. Obviously, you can't transmit frames across a wire that's not actually physically present. So there is a carrier, there's a carrier wave, if you will, that goes across your Ethernet network, and that is how Ethernet knows, hey, I can actually send packets or frames across this media. Multiple access is just what it says. You have multiple computers that can access the same Ethernet network at the same time. You don't have to have one cable run to a single computer, and that's the only computer that can talk on that segment. Although you can do that with some of the higher end switches, but for Ethernet fundamentals, multiple access means everybody can talk just about at any time. And collision detect is a method that Ethernet uses to prevent multiple stations from talking at the same time. So let's talk a little bit about how collision detect works. Basically, it's a flowchart, if you will. First, it senses carrier, basically, is some other station transmitting. No one else is talking, so I can actually start to send my packet. If not, send the first bits of the frame. Was there a collision? And it can detect a collision based upon the fact that there's a higher voltage on the wire than it should be expected. If so, back off, wait a random amount of time, and try again. Now, this random amount of time is really the heart and soul of the collision detection algorithm. If there were a standard amount of time that a workstation waited on the event of a collision, then you would simply have each workstation backing off, waiting the same amount of time, and trying again. In this case, each workstation backs off, waits a little bit for the other workstation to finish sending its data, and then it starts to try to send its data again. And this sounds really kind of unwieldy, but to be honest, all this happens in a matter of milliseconds or microseconds, so you don't really see any degradation in performance from these collisions unless there's like hundreds and hundreds and hundreds of them, like if you have a duplex or speed mismatch on a port, or if you just have a collision domain that's so huge, you've got 5,000 computers in the same collision domain, and nobody can talk because all the broadcasts are always colliding with each other. So if no one else is talking, if there's not a collision, then continue transmitting and just loop through here, send the next bits. Was there a collision? Yeah, there was a collision. Okay, I'm going to back off. I'm going to try sending this frame again. And it keeps doing that, sending a little bit. Hey, was there a collision? Sending a little bit. Was there a collision? Until the entire frame gets on the wire. The best analogy that I've seen for this is that it's kind of like guests at a dinner party. If you've got 8 people around a table and they're all talking, say 2 people start to talk at the same time. Well, they each recognize, hey, I don't need to interrupt this other person. He's trying to talk, so both speakers will stop, and hopefully one of them will time out first, if you will, and start to say their sentence first so that everybody else can listen to it. So lastly, let's move on and look at the layout of an Ethernet frame. Now, here we have the old-style Ethernet up top, and we have the IEEE 802.3, which is the Ethernet 2 standard here at the bottom. And you can see that the frames look pretty much the same. Really, the only difference between the two is this section of the frame right here. In the original Ethernet, this was the type, and in 802.3 Ethernet, or Ethernet 2, this is how long the frame is. And you'll recall that part of the preamble, or part of the other fields in the frame, tell the LLC sublayer of the data link layer what type of protocol is being held in the payload part of the frame, the data part that you see over here to the right. In the original Ethernet specification, this type was encoded directly into the Ethernet frame. And of course, you have the destination address and source address. And of course, you have this frame check sequence at the end. And what that's used for is data integrity. Basically, when a frame is transmitted, the sending station computes the frame checksum and embeds it into the Ethernet frame. It's sent across the wire. The receiving workstation then computes the same checksum, and if they match, then it knows, hey, the frame was not corrupted along the way. If it doesn't match, then at layer 2, the receiving station says, hey, I didn't get all of this frame. You need to resend it. And of course, this is an oversimplification of the Ethernet frame. We'll delve a little more into the inner workings of the Ethernet frame when we talk about VLANs and trunking elsewhere in this course. But for the time being, this concludes our discussion of Ethernet concepts. In this video, we're going to discuss IP concepts. Now, if you want to get really technical about it, IP is a layer 3 protocol, and TCP and UDP and all of the other protocols that reside on top of IP are layer 4 protocols. However, most network engineers, when they're talking about an IP network, even though they're referring to the layer 3 protocol where the IP addresses live, they'll actually use the phrase TCP address or TCP IP protocol. A little inside baseball, whenever I was first putting this slide deck together, I actually called it TCP IP concepts, and then I realized, well, I'm not really talking about just TCP IP, I'm talking about IP in general and how IP works at layer 3. Now again, there are many layer 4 protocols that can be used with IP. The most common ones are TCP and UDP. But if you follow the CCNA and the CCNP certification, you'll find some routing protocols that are their own layer 4 protocol. So they run on top of IP, but they don't use TCP or UDP. However, for the CCENT, all you really need to know about is TCP and UDP and their basic differences. The basic difference is that TCP is connection-oriented. You get assured delivery with TCP, and when we talk about how TCP communications work across the network, we'll show you how that assured delivery works. And you also get congestion avoidance, meaning that if I'm flooding my TCP IP connection, there are mechanisms built into TCP to say, hey, slow the rate down some. I don't want you to flood my upload connection because it will negatively impact my download speed. There's also error detection built in to ensure that the data that's transmitted at layer 4 is actually the data that's received at layer 4 on the other end. Now, because of all this assured delivery and congestion avoidance and error detection, TCP is a pretty heavy protocol. Again, when we delve a little bit into how the protocols work, we'll actually pull up Wireshark and we'll show you the difference between a TCP packet and a UDP packet, and you'll see a TCP packet is generally a lot bigger. As a result, TCP is used for applications where you have to make sure all the data got there and got there in the same order as it was sent. These are HTTP connections for web browsers, for example. These are FTP connections because you want to make sure that when you do an FTP transfer, you actually received the entire file and you didn't drop the middle third of the file, for example. In complete contrast to this, UDP is a connectionless protocol, which means, yes, it's a lot less reliable than TCP. You don't have any of the sequence numbering, you don't have a whole lot of error detection or congestion avoidance. UDP just basically throws the data on the wire. Hey, here's the IP address, I'm throwing it on the wire, hope you got it, because there's no acknowledgement or anything else built into UDP. Again, in contrast to TCP, UDP is a very light protocol, so it's very well suited for things like voice over IP or video streaming. Because the packets are small, for example, and this is getting way advanced from the CCENT, but for example, a voice over IP call using the G711 VoIP codec puts out about 80 packets a second. With UDP, that's pretty simple to do because UDP is pretty light. You don't have to worry about computing checksums and doing all this assured delivery and acknowledgments and all this other stuff like that. It just throws it into a UDP frame and sends it across the network. On the receiving end, again, I'm talking about the same VoIP call, it doesn't matter if out of this stream of 10 million packets you lost 30. It doesn't really matter because by the time those lost packets got there, well, that's part of the conversation that was 5 seconds ago. I don't need to play that back, so therefore I'm just going to drop it. I'm not going to ask the other end to resend it. I'm not going to do any kind of congestion avoidance or assured delivery or anything like that. But again, this is getting some pretty advanced concepts, but it's good to see the difference between TCP and UDP. TCP is pretty heavy. You know the data gets there. UDP, there is no assurance that the data you sent actually got to its destination. So let's move on and talk about one of the most basic concepts with IP, and that is the IP address. IP addresses are logical addresses that uniquely identify an endpoint. And you recall when we talked about the OSI model that the layer 3 addresses are logical, meaning that you can have an IP address and you can assign it to an Ethernet workstation or a token ring workstation or a workstation running frame relay or a WAN protocol. Doesn't matter because IP addresses are logical. They are 4 octets, 0 through 255 each separated by a dot. For example, an IP address might be 192.168.1.104. Now, at the very nitty-gritty, down where the goats graze, as they say here in the South, each octet is 8 binary bits, and essentially an IP address is a decimal representation of a 32-bit number. Now, we'll talk a little bit about binary subnetting, but you won't really need to learn a whole lot about binary subnetting for the CCENT exam. If you get the CCNA and the CCNP and any other certification, you'll live and breathe binary subnetting, especially when you start to design wide area networks. But for the CCENT, you have to know a little bit about them and how they're put together, but you don't need to know how to actually subnet in binary quite yet. Each IP address has a network and a host portion. There are 5 classes of networks, class A through E, but they're rarely used anymore. And when we talk about IP address classes a little later in the course, you'll see why they're rarely used anymore. Now we use what's called CDR, or classless interdomain routing. It uses the number of bits in the network portion of the IP address to determine how to route traffic. And if you've seen any network discussions, you'll see, oh, that's a /26 network, or that's a /30 network, or that's a /23 network. That is CIDR routing. And again, when we talk about how IP addresses are put together, you'll see how CDR blocks are put together, and it'll make a lot more sense. And last but not least, we'll show you this lovely little picture. And this is a graphical representation of a layer 2, a layer 3, and a layer 4 packet. Now you see, at layer 2, it's pretty simple. Receiver address, sender address, how many bytes are in the packet, and the data that's in the packet. This data inside this Ethernet packet, this layer 2 frame, if you will, is IP. You go up to the next level and you've got all the IP bits, and I'm not going to get into all of them here or even in this course. But you've got the sender IP address and the receiver IP address. And then you have the data inside the IP packet. The data inside the IP packet is the TCP or UDP or so on and so forth. Sender port number, receiver port number, acknowledgement number, so on and so forth. And again, if you were to look inside this TCP packet, you'd see information about the layer 5 and higher protocols inside the data payload in the TCP packet. And again, when we pull up Wireshark and you actually see these concepts spelled out for you, it'll make a lot more sense. But this is just kind of a preview of what's coming elsewhere in the course. And that concludes our discussion of IP concepts. In this video, we're going to discuss some switching fundamentals. And essentially, we're just going to go over some of the basic concepts and basic definitions that you'll need to understand switching in general. Now, obviously, this is not an exhaustive list of every definition to do with switching. This is just the things you'll need to know to understand what we're going to discuss in future portions of this course. And some of this will be very basic, but as I mentioned at the outset of this course, I'm not assuming you know anything about networking, because that's what the CCENT certification is aimed at, someone who wants to get into networking. So, all that said, let's start at the beginning. First off, a hub or a repeater. It is a dumb layer 1 device that regenerates every received electrical impulse out of every other port except the one it was received on. So essentially, it takes an RJ45 network or a star-type topology and makes a big shared media topology out of it. Now, collisions are very common on shared media networks because, again, this hub or repeater will not actually examine the frames to see where they need to go. It receives electrical impulses on port 1 and echoes it out ports 2 through 8. And you'll recall from the Ethernet fundamentals that a collision is when 2 devices attempt to talk at the same time. If it receives electrical impulses on port 1 and port 3 at the same time, then the signals from those 2 ports will collide inside the hub and generally slow down the networking speed. Now, we'll see a way to get around that here in just a second. A switch is a layer 2 or higher device that connects multiple devices similar to a hub. If you were to take a hub and a switch and set them side by side, they would look exactly the same. They would have RJ45 ports on the front, they would have little light indicators indicating traffic and connection state, but otherwise wouldn't look different except one will say hub and one will say switch on it. Now again, Ethernet switches can operate at multiple layers. For the purposes of the CCENT, we're only going to discuss layer 2 switches. If you go on to the CCNA and the CCNP and up to the CCIE, if you go that far, you'll deal with layer 2, layer 3, layer 4, all the way up to layer 7 switches. Now the magic sauce inside a switch, if you will, is that a switch maintains a MAC table. It watches all the traffic that comes in and says, well, I see this MAC address on port 2, and I see this MAC address on port 3, and I see these 5 MAC addresses on port 5. It then uses that MAC table to send the Ethernet frames only to the end stations that they are destined for. I've got a nice little visual diagram of how this works in a later video in this course when we discuss switching in depth and exactly how it maintains this MAC table. But at the very fundamental level, a switch is a layer 2 device that actually inspects the Ethernet frames as they come across at the data link layer, at layer 2, and can therefore determine exactly where those frames need to go, whether they need to go out of all ports if it's a broadcast, or whether it needs to go out a specific port or a specific set of ports if it's a multicast or a unicast. And again, we'll get into all of that when we talk about IP, because I'm really using IP terms here. So now you know the difference between a hub and a switch. Let's talk about 2 other concepts that will become very important in future discussions of Ethernet networking. The first is a collision domain. And a collision domain is a segment of the network where Ethernet frames can collide with one another. You remember back to our discussion of a hub, every device plugged into that hub is on the same collision domain. Collision detection is the CD portion of CSMA CD. You remember carrier sense multiple access collision detection. The collision domain is where that collision detection algorithm works. Obviously, collision domains are only an issue with hubs or repeaters. If you have a switch and the switch knows where the frame is supposed to go, then only one workstation will talk on that particular port at a given time, and therefore you don't have any collisions. The other concept that's important to remember is the broadcast domain. The broadcast domain is a segment of the network where broadcasts can reach all nodes on that network. Now, generally speaking, a broadcast domain is the same layer 3 network, the same range of IP addresses or IPX addresses or whatever layer 3 protocol you happen to be running. Now, the magic sauce, to reuse my term, in a switch is that a switch maintains one large broadcast domain, but splits the collision domain up, basically one collision domain per port. So essentially, all of the machines on a given switch or a given VLAN, and again we'll talk about VLANs elsewhere in the course, are all in one broadcast domain. But unless you have a hub plugged into a switch port, each workstation or each network device is on its own collision domain, because the switch knows this MAC address is the only thing connected to this particular port, so therefore this is the only traffic I'm going to send out that port. Therefore, there's no chance for collisions because there's only one workstation or a small number of workstations that could ever talk on that segment at any given time. And so therefore, you can have a greater number of switches in the same broadcast domain because they're all on separate collision domains. Whereas the more hubs you put together, the more repeaters you plug together, will very quickly degrade the performance of the network because they're all on the same collision domain. It's just like people in a big bus. The more people you put in a bus and everyone's talking, the louder it gets, the less chance it is that you're actually going to get the message to the person on the other end of the bus without having to resend it and retry multiple times. And that's the difference between the collision domain and the broadcast domain. The collision domain is everybody talking on the bus all at the same time, i.e. they're talking on a hub. If they're split off into multiple individual collision domains, it's like everybody on the bus has a walkie-talkie and everybody can talk to everybody else, and you don't have to worry about those conversations colliding in midstream. And that covers our discussion of switching fundamentals. So in this video, we're going to talk about basic switch functions, or as I put in the outline, switches. How do they work? First, a bit of review, like I tend to do at the beginning of these deeper concept videos. A switch is a layer 2 or higher device that connects multiple devices similar to a hub. For the purposes of our discussion, we're only going to talk about layer 2 functionality in a switch. Now, the primary functions of a layer 2 switch is to maintain a MAC table, MAC being the Ethernet address or the media access control address, the layer 2 address. It uses this MAC table to send frames only to the end stations that they are destined for. And you might ask, well, how does a switch know? How does it know what workstation a particular frame is destined for? It populates this MAC table by watching the incoming Ethernet frames and remembering what port those frames are seen on. And I've got a little diagram here on the next slide, and it'll make a little more sense if you're more visual like I am. In short, the switch examines the frames that comes through it and forwards them to the destination device. And I've got forwards in bold here, because that's one of those technical terms that we keep going on about. A switch is said to be in the forwarding state when it is actually processing frames and sending them on to their destination. And as we talk about switches more in depth, you'll hear me use the term forwards this frame, and this is exactly what I'm talking about. Now, there are three basic forwarding modes in any kind of network switch. We have the store and forward, the cut through, and the fragment-free forwarding modes. And we'll talk about the differences of those here on the next slide. Now, certain switches can change modes on the fly if needed. For example, let's say a switch starts out in store and forward mode, but after a little while it determines, well, I've not seen any errors come through on any of these ports. I'm just going to switch it to cut-through forwarding and speed up the network traffic that's going through the switch. So let's talk about these three forwarding modes. The first is the store and forward forwarding mode. In the store and forward mode, the entire frame is received in the switch, and the FCS, or the frame checksum, which you'll recall when we looked at the diagram of the layer 2 frame, the FCS is validated to ensure it's a good frame before forwarding it along to the destination device. Now, store and forward is the default operation mode for most Ethernet switches out there. When you get into some of the really high-end, low-latency switches, they may not use store and forward unless you specifically tell it. But most switches, if you were to go buy a switch off the shelf at Best Buy and hook it up into your network, it would be using store and forward mode. Store and forward introduces more latency or delay into the traffic path simply because it does have to receive the entire frame, look at the frame, run a checksum on it, and say, yes, this frame is good, it's destined for this MAC address, and I'm going to forward it out port 7, or whatever port it is. However, the trade-off for introducing this latency is that the switch is highly reliable, as in it won't forward out frames that it knows are bad because it checked the checksum and said, well, this frame is not any good, and so it just rejects the frame right there. Store and forward can also forward between different speed interfaces. Let's say your input interface is 100 megabit and the output interface is a 1 gigabit, or the opposite way around. Because it's looking at every frame that comes through, it doesn't necessarily have to match the speed on both sides. The next switch mode we'll talk about is the cut-through forwarding. With cut-through forwarding, the switch forwards the frame as soon as the destination MAC address is seen, which is about 16 to 20 bytes into the frame. Now, obviously, because the switch is not checking the entire frame, it does not introduce nearly as much latency, and so you will get quicker communications by a few milliseconds using cut-through forwarding versus store and forward forwarding. However, using cut-through forwarding, you have the ability to introduce bad frames into the network. Since the switch isn't looking at the checksum, it just says, well, you're supposed to go out port 7, I'm sending you out port 7, and it's up to the network card on the other end of the link to determine, hey, this is a bad frame because my checksum doesn't match, and tell the sending station, hey, you need to resend this particular frame. We'll continue on with our discussion of basic switch functions and look at the forwarding logic of your generic Ethernet switch in the next video. So we're carrying on with part 2 of our basic switch functions video. We've just talked about store and forward and cut-through forwarding. Now we're going to move on and talk about the last forwarding mode in switches, and we'll also look at our generic switch that we have been talking about over the last few minutes here. So the last forwarding mode we're going to talk about is fragment-free. It forwards the frame after the first 64 bytes are received, which basically puts it as a mix between store and forward and cut-through switching. Now, fragment-free forwarding reduces collisions because the switch can tell after the first 64 bytes whether or not this is actually part of a collision, but it may still introduce bad frames because fragment-free switching still does not examine the FCS in the Ethernet frame. And I'll be perfectly honest, I've been dealing with network switches for over 10 years now. I can't ever recall seeing a switch that's using fragment-free forwarding that either all use store and forward or cut through, depending on configuration and business and technological needs and so on and so forth. Most of them use store and forward just because it's nice to have those error counters in the switch so that you can very easily look in your switch's command line interface, which we'll do here in the next section, and be able to tell, we're getting a boatload of errors on port 27. There must be a bad cable or a bad network card or a bad patch panel. There's something about port 27 that's not right. And you get your cable tester out and you go find out what the problem is. 9 times out of 10, it's a bad cable. But this isn't troubleshooting. This is CCNA, so we won't go too far afield with that. So let's look at a very basic network and look at how a switch makes its forwarding decisions. So let's say we've got 4 computers like so. They are all connected to an Ethernet switch. And there's the MAC addresses. Obviously, these are all fake MAC addresses, but they work for our demonstration here. And these particular workstations are connected to ports Fast Ethernet 01, 02, 03, and 04 on this particular switch. And you can see I'm not very imaginative. The one with all the 1s in the MAC address is on port 1. The one with all the 2s in the MAC address is on port 2. I'm not very creative in some ways, I guess. So as these workstations send packets across the network, the switch learns, oh, all the packets from the 4 MAC address seem to be coming in on port Fast Ethernet 04, so I'm going to put that in my MAC table. And I'm going to remember that all the ones with the 4s are on port 04. All the ones with the 3s are on 03, as an example. So let's walk through the switching decision on a particular Ethernet frame. So workstation 1 over here sends out an Ethernet frame, and it says that my destination address is 000000444444. So this frame makes it to the switch. The switch looks at the destination address and says, well, I've got this destination address somewhere on my MAC table. What port was that MAC address on? And so the switch forwards that frame out to just this workstation on port Fast Ethernet 04. It doesn't send it out to any of the others unless the switch doesn't know what this MAC address is, at which point it will flood it out to all of the ports and wait for one of these guys to say, oh yeah, I've got that MAC address. I'm over here. You send it my way. This workstation over here then replies back, its destination address is all 1s, and the same process works in reverse. I'm going back this way. Hey, you're on port Fast Ethernet 01, and it sends it out to this workstation here. What's really impressive in all this is that, this sounds like something we could do as human beings. The switch makes all of these decisions in microseconds. It just processes hundreds or thousands of packets a second through these switches. And it's still kind of amazing, even though I deal with this stuff every day, that these switches are just so fast, at least in modern times here. And the technology has just increased by leaps and bounds just over the last few years. And that concludes our discussion of basic switch functions. We're going to discuss IP addressing in this video. First, we'll start off with a bit of a review. Now, you saw the slide when we discussed IP basics, IP fundamentals. IP addresses are 4 octets, 0 through 255 each separated by a period or a dot. Each octet is 8 binary bits, so a full IP address is a decimal representation of a 32-bit number. We'll cover binary addressing briefly here in just a moment. Each IP address has a network and a host portion. There are 5 classes of networks. We'll talk about what those are and why they're rarely used anymore. And we'll talk a little bit about CIDR, classless interdomain routing. So first, let's talk a little bit about binary addressing. This is a binary table. In this case, we have the decimal equivalent of 101 shown in binary. And if you've not ever dealt with binary, it can be a bit daunting at first. Essentially, the easiest way to remember this is you start at the right with 1 and you double it with every place in the binary number up till you get 128. By turning on various bits in these 8 fields, you could have any number between 0 and 255. 0 being all zeros and 255 being all ones. In this case, we have 01100101. So if you start at the left and you add these up, 64 plus 32 is 96, 96 plus 4 is 100, 100 plus 1 is 101. There's the decimal equivalent of 101. Now again, this is the very basic discussion of binary addressing. If you go for any higher level Cisco certification or any higher level networking certification for that matter, you'll live and breathe this binary addressing. But now that we know what binary addressing is, we'll move on to the network portion versus the host portion. Now here is an IP address and a subnet mask. The IP address is 192.168.1.1. The subnet mask is 255.255.255.0. Now this delineates out the network portion versus the host portion. In this case, it is a /24 network. It's real easy to see because you've got 3 sections or 3 octets of the IP address of 8 bits each that are the network portion and 1 that is the host portion. 8 times 3 is 24. So therefore, this network would actually be written as 192.168.1.0/24. This also tells you a little bit about how to find the network address and the broadcast address. And again, we won't get into that level of it here in the CCNA, but you can play along at home with the home game by taking a network and a subnet mask, converting them to binary, and then figuring out the network address and the broadcast address. And again, if you do any serious networking at all, you're going to pretty much know how to do this by memory. So now that we've talked about that, let's talk about networks that are smaller than a /24 or a Class C network. And I'm getting ahead of myself already talking about a Class C network. Here is a /30 network. In this case, we have 30 network bits and 2 host bits. Using this formula here, we find out we have 2 host addresses because we cannot use the broadcast or the network address. And so there is the subnet mask in decimal. And this is just another representation of network bits versus host bits. And again, we'll learn a lot more about that when we talk about building an IP network at the very end of this course when we put it all together. But this is where you learn about the basics of IP addressing, network bits versus host bits. We'll pick up with our discussion of IP addressing in the next video. So we're picking up with our discussion of IP addressing. We've just talked about binary addressing. Now we're going to move on into the network classes. The first class of network we're going to talk about is a Class A network. And a Class A network is a very, very large network. It is a /8 network, meaning that the first bit is always 0, so the network ranges are 1.0.0.1 to 126.255.255.254. Each of those Class A networks, 1.0, 2.0, all the way up to 126.0, that is an entire Class A network, which means you have somewhere in the range of 16 million possible IP addresses in each of these Class A networks. Again, we're going to talk about the first bits in the network address, and that harkens back to our discussion of binary networking. The next class of network is a Class B network. Those are medium-sized networks. They're /16 networks in Cedar notation. The first 2 bits are always 10, which means the possible network ranges are 128.0.0.1 to 191.255.255.254. Say that 5 times fast. The third type of network is a Class C network. You can kind of sense the pattern here, can't you? The Class C network is lots of small networks. These are the /24 networks that you probably have run across if you've dealt with any type of small network, or if you've dealt with a home network. By default, they come with a 192.168.1.0 /24 network, so if you've just used its default configuration, you're using a Class C network. The Class C network, the first 3 bits are always 110, which means the possible network ranges are 192.0.0.1 to 223.255.255.254. Moving along to the Class D network, these are multicast addresses, and we won't really talk about multicast very much in the CCNA, but a lot of routing protocols and other layer 4 protocols use multicast addresses. Multicast is where you take one packet, you send it to a special address that's in this Class D network range, and multiple machines can receive it on a network if they're listening to that multicast address. It's different than a broadcast address. If you send to the broadcast address, every machine on the network has to receive the broadcast and has to process it. Whereas multicast addresses, not every machine has to receive this multicast. Where you'll see multicast used a lot, besides routing protocols, is streaming video. If you have a streaming video server and you have multicast clients, that way you can only send one packet across the network and have 15, 20, 30 machines all watching the same video feed. The first 4 bits of the Class D network are always 1110, which gives us possible network ranges of 224.0.0.1 to 239.255.255.254. You can probably guess which network is next. It's the Class E network. Class E networks are experimental. You'll never see these out on the internet. These are really used just for the IEEE to play with networking fundamentals, with new networking topologies and whatnot. The first 4 bits are always 1111, which means the network ranges are 240 up to 255. Like I've said, they're never assigned to internet hosts. So now let's talk about some special address classes that are outside those Class A, B, C, D, E networks. The first one we'll talk about is the automatic private IP address, and you've probably seen the automatic private IP address if you've ever dealt with a network that wasn't working properly. APIPA addresses are used when a DHCP configured workstation can't contact a DHCP server and can't lease an IP address. Now, they're supposed to use these APIPA addresses. Some flavors of Windows will actually just use the last private IP address that at least whether or not it can talk to a DHCP server. That's technically against the RFCs, but it's so widely used and so widely accepted that no one really cares. The APIPA addresses are in the 169.254.0.0/16 network. So that means by default, if you have a bunch of machines that don't have a DHCP server, they'll all get assigned addresses in these ranges, and they'll all be able to talk to each other on a layer 4 level. Now again, these addresses are non-routable. Most internet routers, if not all internet routers, will drop addresses in this range because they realize they're special addresses. They're not to be used for actual internet hosts. The next set of special IP addresses we'll talk about are the private IP address ranges. And again, if you've dealt with any networks, you probably have seen these, but you didn't know why these networks were picked, or you may not know why these networks were picked. They are defined by RFC 1918. And if you're a really big nerd, you can go out and read the RFC 1918. They're freely available. And you can see the logic and the reasoning behind using these address ranges and a whole lot of high-level geekery that I don't even understand most of it, to be honest. But all you really need to know for the CCENT is that these are addresses reserved for non-internet connected networks. Again, like the APIPA addresses, if most internet routers see them, they'll just drop them because they'll assume you're trying to attack them by giving them a non-routable source IP address. Those are the network ranges 10.0.0.0, 172.16 to 172.31, and the entire 192.168 network range. Again, these are within the various existing classes, the Class A, Class B, and Class C networks. So you can have an entire Class A network assigned to your internal network if you want to, just by using this 10 dot. Or you can have a bunch of Class Cs defined by 192.168, 1, 2, 3, so on and so forth. There's another class on here, and I've got this little cheesy doormat here. This is the loopback address range. It's 127.0.0.0. By default, 127.0.0.1 is the local host or the home address, so this doormat here is basically a nerdy way of saying there's no place like home. Hey, everybody's got to have a little humor now and then. And that concludes our discussion of IP addressing. In this video, we're going to discuss the basics of TCP/IP communications, and in this video, we're finally going to break out of PowerPoint for a little bit, and we're actually going to look in Wireshark as a teaching tool for the basics of IP communications. TCP is the connection-oriented layer 4 protocol that makes up the bulk of internet communication. And in this video, we're going to start at the very basics. We're going to talk about the method that TCP uses to initiate the communications and ensure that traffic makes it to its intended destination. So first off, we'll talk about TCP ports. Now, TCP and UDP and several other protocols, but for now, we're concentrating on TCP. TCP uses the port numbers to identify what service on the remote host the traffic is destined for. Ports below 1024 are well-known ports. If you go into Google and search for well-known ports, you'll find that 80 is HTTP, 21 is FTP, so on and so forth. Now this will make a little more sense here in just a couple of minutes when we look in Wireshark and we see with the source port and the destination port. But for now, we're just kind of powering through the facts here. Ports greater than 1024 are available for user services. So if you have a chat server that's not a well-known chat server and you just want to bind it to port 6166, you could bind it to port 6166 on most installations of Linux or Unix or Windows and so on and so forth. Also, any custom-written applications like network management and database servers, for example, may use ports above 1024. They're well known, but they're not actually registered ports, which is the actual term used for the ports below 1024. Traffic originates from a high random port number on the source machine to a specific port on the destination, i.e. port 80 for HTTP, so on and so forth. TCP uses a three-way handshake to establish communications. I've got a little cheesy graphic down here to give you the basic outline of how it works, and then we'll actually look in Wireshark and see how it looks from a packet level. So let's say you've got two machines here, like so, and they want to communicate. So machine 1 sends to machine 2, hey, I'm going to start sending you a traffic. I'm going to set the send bit, which is the synchronized bit, and I'm going to send you a sequence number of 250. This machine over on the right receives the packet and says, hey, I acknowledge that I received your packet. I acknowledge sequence number 250. I'm sending back my sequence number of 400, and I'm sending back a SYN and an ACK, or the acknowledgement packet, to your synchronized packet. And then this machine on the left sends back an acknowledgement that says, hey, my next sequence is 251, which is what you were expecting, 250, 251. And I'm acknowledging that you sent me back sequence number 400, and so on and so forth, back and forth it goes. And I picked low numbers for these sequence and acknowledgement numbers. In reality, they're this huge 32-bit number that's pretty much picked at random, although they do increment by known amounts on just about every operating system out there. These acknowledgments is how TCP knows that the packet got to the remote end. I'm sending you a sequence of 250, and then I send you a sequence of 252. Well, what happened to 251? This machine can then say, hey, I missed 251. Can you resend that particular packet? And this machine says, oh, sure, here's 251, and it resends it. Again, this makes a lot more sense when you get down here in Wireshark. Now, this is a packet capture sample off of my lab network here, and I've included it as part of the work files for this particular course. And we're going to look at these three packets right here. Packets 4, 5, and 6 is the three-way handshake, and you see that going on beyond that is an entire conversation between these two hosts. It happens to be a machine that I have doing recording and my proxy server firewall, if you wanted to know what these two addresses were. So the first thing we'll look at are the port numbers. You'll see that the source port, it's recognized as TIP app server. That's what it's most generally used for, but it's port 3160. Notice it's above 1024, so it's a random high numbered port. Its destination port is HTTP or port 80. So port 3160 on the source is talking to port 80 on the destination. If we delve further into the TCP header and we scroll down to the flags, you'll see this is where the send flag is set. And you can expand that and look at all of the flags available to you. Let me resize this window so you can get them all on one screen here. But you can see all the flags that you can set inside TCP. In this case, the send is set, saying, hey, I'm wanting to establish a connection to you on port 80. If you look up here, you'll see the sequence number. The relative sequence number is 0 in this case. And so let's look at the response. We look at 192.168.15.254's response to this 104. And we'll collapse this and go back up to the TCP. You notice in this case the source port is HTTP because it's responding back to the initial request. Its destination port is 3160 because that's the port that the request came in on. And you can look up here and see that the send ACK flags are set, and we can expand TCP and look at the flags, and you can see that acknowledgement and synchronization is set, and its sequence number is 0, its acknowledgement number is 1. So I saw that you sent me sequence number 0. I'm responding back to say my acknowledgement is 1. My acknowledgement is not 0. My acknowledgement is 1. So if we look at the next packet, which is the ACK to this packet, or the send ACK, again, it's coming from port, scroll up a little, it's coming from port 3160 to port 80 because it's coming from my workstation to the web server, to the proxy server. It says, hey, I acknowledge that you sent me number 1. My acknowledgement number back to you is 1. It's an acknowledgement packet. And then if we followed the flow down through, you'd see that this is actually an HTTP exchange between the two endpoints up until you get this fin packet here, which indicates the end of the conversation between these two endpoints. Again, I can expand this down and we can look at the flags. I'm acknowledging, and the fin bit is set saying this is the end of this conversation. Tear down the connection between us two. And you'll notice up here the sequence number and the acknowledgement number, they've incremented by obviously random numbers because obviously 300 and some odd packets haven't gone between the two hosts. You look at the timestamps, this all happens within just 0.06 of a second. So again, very, very quick. And you can scroll down through this entire list if you're playing along with your own version of the home game, and you can see all kinds of interesting things. Down here towards the bottom, you'll actually see some encrypted traffic for Dropbox and Telnet, and you'll see send resets and so on and so forth, where it was testing out various security mechanisms. For the time being, that concludes our discussion of the basics of TCP/IP communications. In this video, we're going to discuss TCP/IP flow control mechanisms. Now, we have discussed elsewhere in this course the acknowledgement process in TCP. You know that the receivers acknowledge the receipt of each frame, send an acknowledgement back to the sending station, and that the sending station waits for that acknowledgement before it sends more data. That way, you're assured that the data you sent was actually received on the remote end. Now, if you think about this logically, if you sent an acknowledgement back for every packet that was sent, that would be very bandwidth intensive and would cause lots of delays across the network. Because you can imagine you'd basically be doubling your traffic, and not really, because that acknowledgement packet doesn't have a payload, whereas the traffic you're downloading or consuming from the server end does have the payload. But the concept still stands. You have to send an acknowledgement back every time. Well, TCP has a method to control this, and it basically reduces the number of acknowledgement packets required in the TCP flow, and this is called the TCP window. And simply put, the TCP window tells the sending machine, the sending workstation, how many outstanding packets can be on the wire at any given time. And you'll see how that works in the next slide, and we'll actually pull up our Wireshark capture that I've included with the work files, and we'll see this in action. Now, this TCP window starts out as a fairly small number, and this window can grow or shrink depending upon network conditions. And technically, when the window grows or shrinks, this is called a sliding window, meaning that if the sending station is sending too much data at one time, the receiving station can lower the window and say, hey, don't send me so much data all at once. It can slow down the download. And that's basically how quality of service works at this very basic level. And again, quality of service is well beyond the CCNA certification exam, but just a kind of a hint of what's out there if you decide to go down especially the voice and video route. So let's use my pretty little diagram here, because I love diagrams. I love graphical things. It makes me happy to see all the little pictures on the screen. So we have the sending and receiving workstations here. We have the sender on the left-hand side and the receiver on the right-hand side. So we're going to assume that the negotiated window at the very first part of the TCP conversation is 3. And again, actual window sizes are measured in bytes, which you'll see in the Wireshark capture here in a minute. But let's assume that the window that's been negotiated is 3. And so the sending workstation sends the first packet, says window size 3, I'm sending 1. Window size 3, I'm sending 2. Window size 3, I'm sending 3. But for whatever reason, network congestion or, the receiving machine was too busy or whatever, packet 3 is lost. It just never makes it to the remote end. And so the receiving end says, okay, I'm acknowledging number 3 and my window size is 2. Basically saying that I expect your next packet to be number 3. Well, the sending end says, well, I already sent number 3. They obviously didn't get it because they didn't acknowledge that they got number 3. So I'm going to resend number 3 and send number 4. Now, you'll notice that even though this guy is still saying my window size is still 3, you can send me 3 frames or 3 packets before I will send you back an acknowledgement. The sending machine only sends 2 packets at a time before it expects an acknowledgement. So since it sent its 2 packets, the receiving machine says, hey, I acknowledge number 5, meaning that I expect you to send number 5 next. My window size is still 2. And so on and so forth. Window size 3, send 5, send 6. Hey, I'm acknowledging number 7, window size 2, and so on and so forth. So let's look at this in Wireshark, because again, I'm a real big fan of just looking at the packets going across the network. You'll find a lot of interesting things on your network just by doing that. So this is the entire TCP conversation between my workstation that I wrote this particular slide deck on and one of the Ubuntu download mirrors. And I've narrowed it down to just the traffic between this IP address and anything else that it happens to see, which will be the machine that I'm downloading it on. So we'll see the entire conversation set up. There's the SYN-ACK, and the ACK. That sets up the 3-way handshake that we discussed a little earlier in the course. And Wireshark, since it knows pretty much what we're really interested in looking at, gives us all of the pertinent information right up here. You'll see this is an HTTP download of about the first 10 megs of an Ubuntu ISO. So you'll see that my workstation, when it sends the SYN, it says my window size is 8192, or about 8K. The receiving end replies back with its SYN-ACK and says, hey, my window size can be as big as 14,600. And then my workstation replies back and says, well, great, well, my window size is 66,780. So you see the window starts out very small and can grow to be very, very large pretty quickly. The remote end replies back and says, here's my window size, 15,744, and it pretty quickly settles on a window size of 66,780. And after that, you'll notice that the remote end sends 2 frames, or 2 packets, I should say, since we're not talking about Ethernet at this point. It sends 2 packets, and then my workstation at that point then sends back an acknowledgement, and 2 more packets and an acknowledgement, 2 more packets and an acknowledgement. And this goes on for quite a while until we get down here to about packet 421. And I scrolled down a little bit while I was paused just so you wouldn't have to sit here and watch the packets fly by. You'll notice that the Windows 66,780 And then TCP decides, well, after a little while, I can have more data coming across at a given time. So I'm going to up my window size to 229/320 from my workstation. And you'll notice that that goes on for a while. The window size grows and shrinks until very far down in our packet capture here, we start getting duplicate acknowledgments for whatever reason. I'm not really certain what exactly happened, but this happens when you are downloading files from time to time. You notice that the window size still is the same, 262,080, so it makes it past all of that. And then the further down you scroll, you'll notice that the window size suddenly drops right about here. You'll notice that the window size dropped from my workstation. Basically, that's my workstation's way of telling the remote end, hey, I can't handle all this data right now. I'm having to write it out to disk. My IP stack can't handle it. Don't send as much data at one time until you hear back from me saying I've acknowledged it and I can handle more data by use of the TCP sliding window. And of course, if you go all the way to the bottom of the file, you'll start to see all of the send resets where I cancel the download because I really didn't want this ISO. So basically what's happening is the remote end is sending data to me and I'm sending back reset requests saying, hey, the connection's been reset, I'm not accepting it anymore. And this goes on for a little bit and then finally the connection just drops. And again, you've got this entire file in your work files, so you can poke around in there and learn all the deep, dark secrets of how I've got my network laid out. And that concludes our discussion of TCP/IP flow control. In this video, we're going to discuss how IP and Ethernet interact. Now you'll recall that IP is a layer 3 protocol and uses logical addresses, those 4 dotted quads that you're so familiar with, 192.168.1.100, for example. However, at least on an Ethernet network, Ethernet controls layer 2 and uses those burned-in hardware addresses that you've seen if you've dug through Wireshark in any way. It's that big long hex address that we'll see here in our Wireshark capture in just a moment. So you've got these layer 3 logical addresses and you've got these layer 2 burned-in addresses. How do you reconcile the two? Well, the reconciliation method is called the Address Resolution Protocol, or ARP. And every network device that has layer 2 and layer 3 in it maintains an ARP table that maps those layer 2 Ethernet addresses to layer 3 IP addresses. The IP stack on the device uses this table to generate the destination address in the Ethernet frame. Now obviously that works well if the network device already knows about the network address, but if the MAC address isn't known, then a broadcast is sent looking for the destination Ethernet address. If there is indeed a device on the network configured with that IP address, the correct device replies to the broadcast, and the correct address is populated in the ARP table. Now, this ARP table is not static. You can set static ARP entries. Most people don't on their workstations or really anywhere on the network, except in a very few edge cases. So the ARP entries in the workstation time out after a few seconds. Now this happens for a couple of reasons. Number one, if it had to maintain an ARP table of every MAC to IP mapping that it ever knew about, then this ARP table would grow to be huge. But the main reason that this happens is so if you have to apply this IP address to a different workstation, let's say your main file server goes down and you have a standby file server and you power it up and connect it to your SAN and it's back up and running, it's got the same IP address. But for all those workstations that still have the old MAC address mapping in there in the ARP table, they won't know how to get to your new server's MAC address until the ARP entry times out. The workstation then sends a broadcast and say, hey, does anyone have this IP address? And the new server responds back with its new MAC address saying, here's my MAC address. You can start sending all those packets to me. And again, to pull back the curtain a little bit, because I kind of like to do that to kind of give you a teaser of what's in store if you go through the CCNA and the CCNP. If you go down the path of the CCNP and you talk about some of the redundancy protocols, HSRP and VRRP and so on and so forth, you'll see that those protocols provide redundant services at the network level by basically spoofing a MAC address. And again, that's way outside the realm of the CCENT. So that's something you can research on your own time if you'd like. So let's look at my workstation here. So I've got a DOS prompt pulled up here. I'll pull it up here in the middle so everyone can see. And I'm going to show you what the ARP table on my workstation looks like. So on a Windows box, you do ARP-A, and that gives you the ARP table on this particular workstation. Now you can see here's my internet address, 192.168.101. And here's the physical address that corresponds with that IP address. Here's the broadcast address. You notice that the broadcast address is all Fs because it is a broadcast. It's all ones. Just like the super broadcast is what I call it. The all 255's address is all Fs as well. You'll notice that these are static ARP entries, but they're put there by the system. You normally won't have to enter the ARP commands to set up a static ARP yourself. And just to further drive the point home, we'll pull up Wireshark here, and I've got a packet highlighted that is an ARP packet. This was my workstation, 192.168.1.104, and what I did is I manually cleared the ARP table. If you want to play along at home, you can do this by doing ARP-D for delete and hit star. That kills the entire ARP table. If you look at the ARP table now, you'll notice that there's only one MAC address in there. It happens to be my default gateway out of the network. And if you hit up arrow and run the ARP command again, you'll notice that all of those dynamic and static ARPs come back into the ARP table because it's having to communicate with all of those servers and workstations. So at a packet level, this is what it looks like. Here's my workstation sending out a broadcast saying who has 192.168.1.240 tell 192.168.1.104. This is an ARP request. It's coming from my Ethernet address to the broadcast, the all ones. And you can dig down in here and look at all of the bits and bytes inside the packet. Generally, all you need to know about this ARP request is right here. And the next packet that you see there is the reply coming from this tie-in comp, which happens to be the server sitting over in my lab, saying 192.168.1.240 is at this MAC address. You'll notice that in the ARP resolution protocol, it's a reply, and it says, here's my sending MAC address and my IP, and here's my target MAC and IP address. So again, ARP is a very, very simple protocol. It's kind of the glue that holds all of IP together, to be honest. And that concludes our discussion of how IP and Ethernet interact. So we're going to round out our overview of IP, and we're going to talk about some basic TCP/IP services, namely DHCP and DNS. And we're discussing them at this point in the course just simply because DHCP and DNS are pretty much ubiquitous. You're going to find them on any network you happen to run across. In fact, a lot of people may be running DHCP at home and may not even realize it just because it's built into so many of these consumer-grade routers and switches and so forth. So, first a little bit of review. You'll recall IP is a layer 3 protocol and uses logical addresses, meaning that the logical address is not tied to any specific device. These logical addresses can be moved from device to device. You can have certain addresses that represent multiple devices, or multiple addresses all bound to the same device. So the question comes up, if these are logical addresses, how do you configure them? Well, the first way is the most obvious. You can go to every workstation on your network and manually set an IP address. That works good if you've got 5 workstations and you have complete control. But if you have 5,000 workstations spread across 6 states and 2 countries, then that's not really a workable solution. You'll have spreadsheet after spreadsheet of what IP addresses are assigned to what users and what servers and what workstations, and it's just a huge pain in the backside. No, you'll want to use the Dynamic Host Configuration Protocol, or DHCP. Now, simply put, a DHCP server is configured to hand out IP addresses. You go into the DHCP server and you say, this is my pool of addresses. I want you to start at 192.168.15.5, and I want you to hand out addresses from .5 all the way up to .200. And when you hand out this IP address, hand out this default gateway and these DNS servers and this domain name. And you can also configure other different parameters inside the DHCP server. If you get into Cisco Voice, you'll use an option to tell your Cisco phones, or any voice over IP enabled phone actually, what server to get its configuration information from. But again, this is an overview, so we won't get too far into that. So we'll give you a basic overview of how DHCP works, and then we'll pull it up in Wireshark, and we'll actually look at the protocol level. So, say you have a server and a workstation here. This is your DHCP server over on the right, and this is your workstation on the left. This workstation powers up, it initializes its IP stack, and realizes, oh, I'm configured for DHCP. I'm going to send out a DHCP discover. Hey, I'm here on the network. What DHCP servers are out there on the network? Now this is a broadcast. It goes to the all ones address in Ethernet, and you'll see that when we pull it up in Wireshark. Now what that means is that your DHCP server and your workstation have to be on the same physical piece of wire, or you have to have a DHCP helper relay configured in one of your routers. Now, DHCP relaying is not really covered in the CCNA course other than to realize that it's there and it exists as a thing. But what's important to realize is that this DHCP discover is a broadcast. The DHCP server then replies back to your workstation with a DHCP offer. Hey, I can service your DHCP request. Now, if you have multiple DHCP servers on the network, this workstation may get multiple DHCP offers back. Most organizations only have one per network. It just cuts down on confusion. So once this workstation knows the MAC address of a DHCP server or multiple DHCP servers, then your workstation sends out a DHCP request. It asks the DHCP server, okay, I picked you to service my DHCP request. Can you give me an IP address? Now there's a few different ways this DHCP request can go down. If this is a workstation that was already on this network, let's say it's a workstation that physically sits under someone's desk, so it's not ever going to move. It's going to make a DHCP request, and it's going to tell the DHCP server, here's the IP address I already have, can I just keep this DHCP address? And most of the time the DHCP server will reply back and say, yes, you can keep that IP address. If it's not ever been on this network before, or if its configuration has been cleared, it may say, I don't have an address, just pick one out of your pool and hand it to me. In either case, the DHCP server will reply back with a DHCP acknowledge. And inside this DHCP acknowledge is where the IP address, default gateway, DNS servers, domain names, and any other DHCP options are communicated back to the workstation. So as promised, here is a DHCP capture inside Wireshark, and this file is available as part of the work files for this particular course. Now you'll notice there's 4 packets here, just like in our example. The discover, the offer, the request, and the acknowledge. So this is what happens. This workstation, in this case, it does not have an IP address. Its source is all zeros. Its destination is all 255s. It's broadcast. You look down here and you can see on the Ethernet, the destination is broadcast. DHCP discover, and it has a transaction ID so that it knows what the answer is for. So it sends out a DHCP discover and says, hey, I am looking for a boot server, and technically it's an extension of boot here, the boot protocol. And if you'll notice down here, it is not actually requesting an IP address. It does not have an IP address on this network. So the DHCP server replies back, in this case 192.168.0.1. It's going to offer it the address of 0.10, but it has not accepted that yet. So that's the destination address, but if you look up here in the Ethernet, you'll see that it unicasts it back. So the broadcast comes from the workstation, and the DHCP server then replies back to this workstation. Since it knows what the MAC address is, it can direct it directly to that workstation. So it replies back, and it says, hey, here's the address you had. Here is my address that I'm going to give you, and here's my server address where it's coming from. And you can look down through here and you see the subnet mask and the renewal time and the rebinding time. We won't get into how the leases work in DHCP. We're just stepping through the packets just so you can get a better idea of how it works. At this point, the workstation replies back to the server and says, okay, you offered me this address. I'm going to actually request this address now. And of course, the DHCP server replies back with an acknowledgement saying, yes, you can actually keep that address. You notice that even at this point, it's still saying the client IP address is all zeros, but it says you can keep 192.168.0.10. And at that point, IP communications can be established. We will pick up in the next video and discuss DNS. So we're continuing on with our discussion of basic services. We've just covered DHCP. Now we're going to move on to DNS. And again, to review, just like we did with DHCP, if you're just joining us, IP is a layer 3 protocol, uses these logical addresses. Logical addresses can be moved from device to device, and computers don't understand human readable names. If you go and ask your computer, hey, where's yahoo.com? The computer's going to go, I don't know. I don't understand names. All I know is IP addresses and routes and binary. Computers are pretty dumb when you get down to the fundamentals. All they really understand are zeros and ones. So, given that these are logical addresses and they can be moved from device to device on a whim, how do we find a specific device if this IP address can change on a whim? Well, you can write down the IP address of every computer you'll ever access. That's not a workable idea because, you don't want to have a notepad here. Oh, I want to access Yahoo. Let me flip over to the Y's. There's yahoo.com and put that IP address in there. You could take that one step further and use a local hosts file, which is valid for some certain types of network configurations where you may not want a host name in DNS, or you may not want a specific host name in DNS. But most of the world uses the domain name system, or DNS. And quite simply, a DNS server is a server that translates human-readable names to IP addresses. And again, I've got a little diagram here, and we will look at a packet capture for DNS here in just a little bit. You've got your server and your workstation here, and you want to access google.com. So you go into your web browser and you type www.google.com. Well, as part of DHCP, there's how it all dovetails together again. Funny how that works. As a part of DHCP, you were given a DNS server's IP address. So whenever you want to access google.com, your workstation goes to the IP address of that DNS server and asks that DNS server, hey, what's the IP address for www.google.com? This server here goes off on the internet and actually finds the address for google.com and replies back, www.google.com is 74.125.134.106, or at least it is from my network as of right now. Your mileage may vary depending on your part of the country or part of the world, obviously. Your workstation then takes this IP address, which is what it understands, and uses that to initiate a connection out to google.com. Now you recall that since you have the IP address of the DNS server, you don't actually have to do a DNS lookup to get the name of your DNS server. So as promised, let's look at a Wireshark capture file. This is the dns.cap file that's included with the work files. And in this case, you'll notice that our source, our workstation, is 192.168.170.8. This is the DNS server, 192.168.170.20. Now this is a freely available Wireshark capture file. So there's all kinds of interesting DNS lookups in here. Again, we're going to ask a standard query for the TXT record for google.com. So here's the domain name system query. We are asking this DNS server here for DNS information for the domain google.com. You'll notice that it is UDP in this case. You notice we use UDP because these DNS lookups have to be very, very quick. You don't want to have to wait 30 seconds for your DNS response to come back. The DNS server then replies back and says, here is your query response. And of course, we have all kinds of different flags about authoritative and recursive and so on and so forth. The DNS server actually replies back with the query, here's what I'm answering, and here is the answer. Google.com, type TXT, here's the TXT record, you get the time to live and the data, so on and so forth. You then ask for the mail exchanger for google.com, and here's the mail exchangers for google.com, and you can poke through this file pretty much at your convenience. You've even got some IPv6 lookups in here, and we will briefly talk about IPv6 towards the end of this course, just to acknowledge that it does exist. But otherwise, DNS, at this level at least, is pretty straightforward. You make a request of the server, and it answers that request. And that concludes our discussion of basic services, DHCP and DNS. So we're going to change gears a little bit, and we're going to take a few minutes and talk about network security. Now, to be honest, network security is an entire subgenre of IT in and of itself. Like network engineers are different than programmers, are different from network architects, are different from telephony people, or different from network security folks. And as I've been saying, and you're probably sick of hearing it by this point, this is the CCENT, and we're not going to get a whole lot of exposure to network security in this course. But it is on the exam, at least the little bit we're going to go over here, and so as a result, it's in the video here. Now, a good network engineer will keep security in mind when he's designing his network. Again, even though we may not be security experts or security analysts or may not be responsible for all of the data security on the network, we still need to keep it in mind because in reality, network security is kind of a balancing act. As an example, if I were to take my laptop and power it off and shove it in a drawer and lock it, I could say there, my laptop is 100% secure. It is completely closed off from everything. No viruses can get on it, no spyware, no malware, nothing can get on it. However, it's just a big, heavy paperweight at this point. I really can't use the laptop for much of anything because it's completely isolated. In much the same vein, you can completely isolate your network from any clients, from the internet, from anything outside your walls or outside your direct control. But, that's not really workable as a functioning network. I mean, we have email, we have streaming video, we have business-to-business VPN connections, we have client VPNs, remote workers, teleworkers. And locking down the network completely is just not a good method of securing your network. Conversely, you can't leave everything completely open either. You can't just say, well, there's no point in dealing with passwords, there's no point in dealing with proxy servers or filters or virus scanning. That just slows down the network. Let anyone do anything they want. You do that and you're probably certifiably insane because your network will not be worth anything in about 2 weeks once everyone discovers that, hey, I can go out to whatever website I want and download whatever I want and put it on my computer and I have admin access to Active Directory and everything on the network and you just won't have anything anymore. So it's important to keep security in mind, but realize you have to walk that fine line between usability and security. You can't make the network so secure that your users can't get their job done because they're constantly having to type in passwords and, oh, well, I can't actually get to the internet on this computer. I have to go over to that computer over there and download my files and put them on a floppy disk or a CD or a thumb drive and bring them over to this computer. You can't lock it down that far, but you can't go the other direction either. Now, I know some of you, especially if you're just starting out in networking and you're dealing with a small company, you may be thinking, why would anyone even attack my network? I'm not some Fortune 500 company. I don't deal with nuclear launch codes or anything like that. Why would anyone really care? Well, there are several reasons for external attacks. The first is corporate espionage. Even though you may not be a huge corporation, you may fit in a niche that deals with some pretty sensitive information that doesn't really need to get out. For example, the company that I currently work for has about 600 employees. So again, we're a good mid-sized business. We're not a Fortune 500 company by any stretch, but we deal with protected health information on a daily basis as part of our business model. And so, therefore, if someone's going to attack our network for corporate espionage, if they were able to crack into our network, they would get access to a wealth of information that they could use to poach our customers away from us or just perpetrate some kind of scam against our customers or our clients. So that's the big reason for external attacks. Another one is a denial of service. I'm not going to take your information, but I'm just going to make it where you can't do business. And therefore, if you're not doing business, you're not making money and you'll go out of business. Admittedly, the denial of service or the distributed denial of service or the DDoS attack is kind of the new hot thing here lately with all the anonymous and the script kiddies out there. Let's just get 50 million computers and point them at this network and just turn them loose and we'll just deny service to everybody running out of that same data center and no one will get any work done. Another reason for external attacks is not really an attack, but information harvesting or to run a botnet using the computers on your network. And again, you can harvest names and passwords and confidential information that happens to flow through the computer. Or you can just run a botnet and churn out spam or anything else like that. And what I consider to be the lamest reason for external attacks, but is probably a lot more prevalent than a lot of people would realize, is because I can. Well, why did you do that? Well, because I can. It's kind of like talking to my kids. Why did you do that to the dog? Well, I shaved him because I could do it, because he was there. They're not after any corporate information. They're not really wanting to deny you service. They just went and defaced your website because it was there and they felt like it. Now, external attacks are not the only method of attack on a network. There are other methods of attacking a network. And honestly, more attacks on a network takes place from inside, whether it's purposely or not. And some of the things to look out for on the inside of your network is infected devices being brought in. And as the BYOD, or the bring your own device phenomena, gets more steam and people are bringing their own laptops and cell phones and whatnot onto your network and expecting to use them, they may not have up-to-date virus definitions. They may not have up-to-date spyware definitions. They may not be running antivirus at all. And if you don't have a policy in place to check those machines before allowing them onto your network, they could be bringing in anything onto your network. And that's where a lot of these internal attacks come from. The next is toolbars and freeware. Hey, I want the little Bonzi Buddy. That was popular about 15 years ago. I want Bonzi Buddy, or I want WeatherBug, and I'm just going to download, hey, it's free cursors, it's free screensavers. I'm going to download it onto my computer. Now I'm part of a botnet. Now I have a virus. Now I have a keylogger, so on and so forth. In fact, an interesting anecdote that I read involved a company that was doing penetration testing at a credit union. And what they did is they took several USB thumb drives, and with the company's permission, of course, they put a keylogger and a little phone home application on these thumb drives and set it to auto-run whenever it was inserted, and just left it laying out in the parking lot. And they said you were surprised at how many people picked up those thumb drives, took them into the building, and just plugged them into their corporate computer. Oh, look, a free thumb drive. I wonder what's on it. Plug it in there. Now you're infected. And last but not least, you can't rule out disgruntled employees. You know, this entire department is being laid off, so you know what? I'm just going to go in and I'm just going to erase all the routers and reload them and take the entire network down on my way out the door. Now, hopefully, most people are mature enough to not do that, but there have been a few cases. There was a network administrator in San Diego a few years back that he built the network. He was getting ready to get laid off, so he just took all the passwords with him and wouldn't give them to anyone. To be honest, people like that really irritate me. They give the good network engineers and the good network administrators a bad name because of the actions of a few rogue agents, if you will. But those are some of the more common attack vectors, and as we discuss network security, we'll discuss some ways to mitigate these attack vectors. But for now, this concludes our overview of network security. We're going to continue with our overview of network security, and we're going to discuss some common network threats. Now, like with anything in computer networking, there's several different types of attacks on a network. These can range from everything from a denial of service or an electronic attack from people that are in other cities or even other countries, to people walking into your facilities and trying to walk out with your network equipment and your servers. And we're going to discuss some broad categories of network threats and network attacks. Now, obviously, this is not meant to be a comprehensive overview of network security, but it's enough to get you thinking about the steps you need to take to secure your network and some of the potential shortcomings in your current network security model. So the first type of attack we're going to talk about is a denial of service or a distributed denial of service attack. Now, I have a very simple diagram over here on the right, and if you've never actually heard of a denial of service attack, or maybe you've heard of it and you're not exactly clear on what it is precisely, then this should serve to help you out some. Essentially, we're the victim in all of this. We are the network that is getting attacked through this denial of service attack. You have the attacker, which harnesses several zombie computers, and these may not necessarily be unknowing zombies. It could be an anonymous type of attack where, hey, let's try to take down Bank of America, which they tried to do here recently. And so we'll all sign up and run this client on our computer, and we will let this attacker and these handlers tell the zombie computers where to attack. Now, this type of attack used to be pretty uncommon, but with the advent of ubiquitous broadband everywhere, it's becoming more common. Again, it's kind of hard to do a denial of service attack when you have a dial-up connection or an ISDN connection, but now that broadband connections in the home are getting so high speed, 10, 15, 20 megabit, it's very easy to take just a very few computers and completely overwhelm an internet presence. Now, with these few computers, the attacker floods your network with traffic, just garbage traffic. It could be legitimate web requests, it could be just trash on the wire, it could be anything. And the net effect of this is that it consumes CPU and bandwidth on your routers and your servers and your switches and your workstations if it gets down to your workstations. It prevents legitimate traffic from making it across your network. For example, if someone's going to run a DDoS attack against a website, then you have 5 million machines all making web requests of the same web server. The web server will fall over from the load. Or if the web server can keep up with the load, then you may consume all of the bandwidth resources or all of the CPU resources in the router, having to keep track of all of those connection states. Now, to be honest, a denial of service attack is not really a major security concern, but it is a pain in the backside because your network is essentially shut down. Even if it's just your internet presence, most companies nowadays pretty much require an internet presence. I work for a mid-sized company. Obviously, we're not doing e-commerce with thousands of individual end users, but we do have clients of ours that connect through VPN connections to transfer files back and forth. And if someone was running a denial of service attack against our internet provider and consumed all of our internet bandwidth with just garbage traffic, then our clients wouldn't be able to connect to our network. To be honest, mitigating a denial of service attack is very difficult because, again, this traffic is coming not just from one or two computers, but from thousands of computers. And so you can go into your router and you can create access lists, but each one of those access lists that deny the traffic will consume CPU resources on the router. Again, pretty much the only way to survive a DDoS attack is just to wait it out, and that's not really the best scenario most of the time. But if you have a truly widespread damaging denial of service attack, there's not really much you can do to prevent it. So that covers DDoS. We'll pick up with our other common network threats in the next video. So we're continuing on with our discussion of common network threats. We've just talked about denial of service. Let's move on to the other types of network threats that you'll run across. The next type we'll talk about are reconnaissance attacks. Reconnaissance attacks aren't really destructive attacks like denial of service in and of themselves. They are usually a precursor to a denial of service or an access attack. The best way to think about a reconnaissance attack is like a burglar casing the joint. If someone's going to break into your house, generally they're not just going to walk up and break the window and walk in. The burglar will take time and watch and learn. He leaves for work at 7:30 and his wife leaves for work at 7:45 and drops the kids off at school on her way to work. And so no one's in the house from about 8:15 to about 3:30 until the kids get home. And he'll watch your neighbors and figure out when your neighbors are there. He'll pick the best time, given all of the information that he can gather from watching you, and then use that information to his advantage to attack you at your most vulnerable. And honestly, that's precisely what a reconnaissance attack is. The first thing they usually do is they'll snoop around the network looking for IP addresses that respond. They'll figure out this is your public IP address range. This is outside your firewall. So you know what? I'm just going to run a ping sweep. I'm just going to ping every device on your subnet. I'm going to see which ones respond to a ping. Those that respond to a ping get examined for vulnerable services. They'll use a tool like Nessus or Nmap or any number of vulnerability scanners to interrogate any open ports and any open IP addresses for any type of vulnerability that may be out there. Let's say there's a buffer overflow in a particular version of SSH that you're using that allows you to get root access. Or let's say you're running a website that's vulnerable to a SQL injection attack. These tools will give you a pretty comprehensive report of exactly what's going on your network and exactly what's wrong with your network. And to be honest, they can be used by us as the good guys as well. We can take these tools, run them against our own network, and discover, oh, this particular executable is vulnerable and it needs to be patched, and here's the patch for it. The bad guys, however, take all of this information, they gather it all up in one big pile, they decide the best way into your network, and they'll use all of the information they gathered in a reconnaissance attack in a later attack all at once when you're not really expecting it. They'll do it at 2 o'clock in the morning local time when there's not someone sitting there watching the network and watching the servers blow up and go down. And depending on what kind of network monitoring you have in place, they could have free run of your network for 3 or 4 hours before you wake up and figure out what's going on. So that leads us to the last type of network threat, which is an access attack. An access attack, as we've mentioned previously, usually follows a reconnaissance attack. An access attack will exploit a vulnerable service and cause it to malfunction, thereby giving more access than the service was originally designed for. You heard me mention SSH on the previous slide. That's actually a very good example. There was a flaw in a specific version of SSH about 5 or 6 years ago, that if you ran SSH and allowed root login, then this particular version of SSH would accept any password as the root password. Needless to say, that is not really how it's designed to work. Now, those of you that are doing professional network security would probably just had your head spin around. You don't allow root access through SSH. You don't allow root logins remotely. You only allow root to log in from the console. But if your sysadmin is lazy or ignorant, they may just turn that option on in the config file, and they've just opened up that server and potentially everything else on the network to an attack from an access attack. Now, a password attack is also a type of access attack. Some people will split it up because technically you're not really exploiting anything in a password attack. But a password attack is when an attacker attempts to guess a username and a password to gain access to the network. You've probably done a password attack yourself when you've gone to a website and forgotten your password. Well, is it A? Is it B? Is it C? You've got your list of passwords that you generally use on websites, and you keep going down the list until you find one that actually works on the website. Obviously, that works for you as the actual owner of that username and password combination, but the bad guys can also use that method of access to get on your network whenever they really shouldn't. We'll talk about how to mitigate that in the next video, protecting the users from the scum of the network. But for now, that concludes our discussion of common network threats. So let's carry on with our discussion of security and talk about protecting the network, or as I put it in the title, protecting the users from the scum of the network. So over the past few videos, we've talked about who wants to attack us and why they might want to attack us and how they might carry out those attacks. So how do we protect the users and our network infrastructure from these attacks? Now we'll talk about some specific methods you can use for securing various parts of the infrastructure, but it basically boils down to defense in depth. Basically, don't depend on just one layer of defense to protect the network. A lot of people will say, oh, well, I've got a firewall out in front of my network. That's going to be good enough. Well, what happens if someone happens to get past that firewall? Let's say they compromise a web server that sits behind that firewall. Now they have control over a web server that might be sitting right on the inside of your network, and they can use that as a platform to attack further inside your network, attack other machines, attack your network infrastructure, and so on and so forth. So you want to practice defense in depth. Basically, you protect the perimeter. You set up a firewall, you set up proxy servers and NAT and reverse proxy. And again, I'm not going to go into a whole lot of detail on exactly how to set all of that up, but just know that you have to protect the perimeter. You have to protect your off-site connections, protect your internet connection. Make sure that you have a good, strong router out in front of your internet connection that could handle a potential DDoS. And maybe even use an intrusion detection system or an intrusion prevention system to automatically blacklist certain IP addresses when they start behaving badly. You protect your workstations. You make sure that all of the software is up to date on your workstation, so that way if someone does happen to make it past the perimeter and make it past your internet connection, then it's going to be more difficult for them to find a foothold on your workstations because they're all patched and they're all running the latest version of the operating system patches and the application patches. And obviously you have to protect your servers. Make sure that they have all of the necessary patches. Make sure that they're configured to only allow connections to the other machines that they need to connect to. If you have a web server that has to talk to a database server, make sure that that database server only accepts connections from the web server and from whatever other administrative workstations you might need to manage that database server. So now let's talk about a few specifics. Step one will be firewalls. And a firewall in a computer networking context is much like the firewall in a car. It protects you from the engine, somewhere you don't really want to be, and it allows certain connections between the inside of the car, the steering wheel, the turn signal, the radio, and the engine compartment to control the way the car moves, to control the throttle in the engine, to control the electrical system. In a computer context, firewalls sit at the perimeter of the network, and they only allow specific connections to specific machines. We'll discuss exactly how that works, and I've got one of my patented diagrams here at the bottom of this slide. You'll see that in a few seconds, and it'll make a little more sense then. Firewalls can reduce the likelihood of access attack, because honestly, if they can't get into the network, then they can't try usernames and passwords. They can't run one of those network vulnerability scanning tools that we mentioned in the previous video. The next step is to set up what's called a DMZ, or a demilitarized zone. And once again, the computer world takes terms from the real world, if you will, and uses them in a networking context. A DMZ is just like it is between North and South Korea, at least as it is between North and South Korea as of late 2012. It's an area where no one really wants to go. It's an area that's not quite in the enemy territory, and it's not quite in our territory. It's kind of a middle ground where we can meet if we have to. Here's one of my patented diagrams that I just mentioned. So you have a machine out here on the internet, and it needs to access a server that's inside your network. Well, you could just allow a direct connection from this workstation on the internet to your server. And if this is a web server, they will attach to port 80. However, if this is a Windows web server, you probably are running lots of other protocols on this guy as well that would be exposed out to the internet if you just left it out there for all the world to connect to. A DMZ involves putting a firewall between this web server and any other machines that are inside this DMZ. Let's say that this web server has to talk to a database server. And so this database server can sit out in the DMZ. However, the firewall does not allow access to the database server. But let's say you have to have access to resources inside the network, and that's where the second half of the DMZ comes into play. You have another firewall that protects your internal network, and then these servers in the DMZ can talk to mainframes or other servers inside the network or to video conference systems. At least those are the examples that I have here. And obviously any traffic coming from inside your network, since it's coming from a more secure zone, can pass out right through both of these firewalls out to whatever hosts on the internet they need to access. We will pick up with our discussion of protecting the network in the next video. So we are continuing on with our discussion of protecting the network, and we're going to move on and talk about network protections. Now, we've talked about protecting the outside connections. This is a discussion of ways to protect the internal network infrastructure from any potential access or hacking attacks. Number one, make sure that everything on the network is running current antivirus. Again, that seems kind of like a no-brainer, but you'd be surprised at the number of small networks that I walk into. And I'll log into a server, maybe their main file server, and hey, where's the antivirus? Oh yeah, we just never installed it on there. It slows the main file server down. It's like, I just want to take you and smack you around a little bit, because this is where everyone's putting their files. If someone puts a virus-infected file on your main file server, then everything on that server is potentially suspect. And again, it's not enough to just have antivirus installed. It needs to be updated because new threats emerge in the landscape all the time. And if you are running outdated antivirus definitions, then that's almost as bad as not running any at all. The next step is to enforce password security. And you'll recall when we talked about access attacks, we discussed a user that had forgotten their password and they're just trying every password. Well, I'll try this. Oh, I changed it. I'll try that. I'll try the other password. If you have proper password security, after the user tries to log in incorrectly 3 or 4 times, their user account will lock out and may send an email or may give some other indication to network management that, hey, this particular user account was locked out because of too many incorrect passwords. Now, it could just be a user that changed their password, went on a week vacation, and can't remember it when they come back. Or if it happens at 2 o'clock in the morning, it might be someone trying to log in using a bad password or an outdated password. Another method of enforcing password security is making sure that passwords change every so often. This way, if a user's password is compromised, it's only good for a certain number of days before they have to change it. The third step of enforcing password security is to make sure that they use complex passwords. Don't let people just use their username as their password, or the word password, or password123. Active Directory by default, with Server 2008 and above, requires complex passwords. It can't be the same password you used 2 passwords ago, and so on and so forth. The third step in protecting your network is to secure your routers and switches. And we'll talk a little bit more about exactly how to secure routers and switches when we discuss routers and switches elsewhere in the course. But basically, just use some common sense. If you have a switch that's sitting out in an exposed location, disable any ports that aren't in use on that switch. If you have a router that is accessible to really anyone, secure that router. Use SSH. Make sure it has a good enable password. Make sure that it is running some type of network security on the device so people can't use your routers and your switches as part of a reconnaissance attack. And step 4 is physical security. And a lot of people overlook physical security, but there's an adage that someone who I respect a lot that works in security taught me a long time ago. And that adage is, if I have physical access, I win. If I can walk into your data center, pick up your server, and walk out and take it back to my back cave so that I can hammer on it and try to crack the passwords, all of the security in the world on that box is not useful. Because yeah, you're out of server or you're out of laptop, and that's generally the biggest attack vector for physical security. But someone steals my laptop and it's got a file on there that's got our IP scheme for our network, or it's got a list of network passwords for our network equipment. Any encryption can be broken. It just takes longer for some of the higher levels of encryption. But this is the one thing, if I can enforce or impress on you in some way, is make sure you have physical security. Also, educate your users about social engineering. Social engineering is part of the reconnaissance attacks that we talked about earlier in the course. But social engineering is calling up the help desk and saying, yeah, I'm here working on the CEO's computer, and he's left the office and I need his password so I can unlock it and check it. Well, hopefully your help desk is intelligent enough to know, let me talk to the CEO, or let me call him on his cell phone to make sure that, he actually needs you to unlock his password. There was a news story just recently about a journalist who basically had his Twitter account and Facebook account hacked. They wiped his iPhone and his iPad and all of his devices, And they used social engineering. They basically called up Apple and pretended to be the user and said, yeah, I forgot my password. Here's the last four of my credit card number. Can you reset it? And then they logged in with that password that they just reset, changed the email address, and just all snowballed from there. You can go Google it up if you're interested. But your users need to be aware that sometimes if you see someone in the building and it doesn't look like they shouldn't be there, challenge them. Make sure that that's not someone that's just walking in trying to dig through garbage cans or look under keyboards for passwords. And finally, enforce physical security to sensitive areas. Don't let anyone just wander into your data center. Make sure that the access to your data center and your wiring closets is locked. Lock the door. Don't just leave the server rack just sitting out in the break room for anyone to walk by and plug up to. And again, to experienced network engineers, a lot of this is old hat. But to people that are just starting out, some people may not even think about physical security. Well, what good does it do them if they go take this router? Well, now if they can crack the password on that router, now they have your configuration, which may have WAN configuration information. You may have SNMP community strings. You may have local passwords on that router or that switch that they can then use as part of a reconnaissance or access attack against your network to try to gain more access than they should. And since they're the attacker, the access they should have is zero. So that concludes our discussion of protecting the network. So in this video, we're going to talk about basic interaction with the Cisco command line interface. Now finally, after all of these slideshows we've gone through and all the basic knowledge we've gathered up to this point, we finally get to interact with some actual Cisco hardware. So let's get started. Normally, when you connect a console cable to a switch, much as I have here to my Cisco 2960, you will get this interface. It tells you that the console is available. Press return to get started. This switch has absolutely no configuration on it, so it is as vanilla and as generic as we're going to see. And of course, we will go through the process of configuring it and getting it up and functioning on the network elsewhere in the course. But this video is just about how to interact with the command line interface. Now, normally when you log into a switch, you are presented with what's called the user exec prompt. And you can tell it's the user exec because it has this greater than sign as the last character of the prompt. Now, the Cisco CLI is very straightforward. We'll just dig in here and show you some of the commands you can use and some of the ways you can interact with the command line for command line editing. Your best friend in this situation will be the question mark key. You enter question mark, and you get commands that are valid for your specific context. In this case, we've not started to enter any other commands, so we see all the commands that are available to us. And obviously, since we are in user exec mode, these commands are a subset of all of the commands available to configure the switch or check the status or so on and so forth. Now, if we start to enter a command, for example, if we enter show and enter question mark after show, it shows us everything that's valid for the show command. In this case, we can do show crypto or show EPM or show flash. One of the things you'll notice if you've dealt with any Cisco hardware is you don't see the run command in here. Normally it would be right here after RMON, but because we're in user exec mode, we don't have the option to show the running configuration. Now we can show inventory, for example. So if we do show inventory, obviously the inventory in a fixed configuration switch will be the switch, which is a 296048 port, and this gives you the serial number, the part ID, and so on and so forth. Not really anything that's useful in most cases. On a router, that's a little different because you can actually do show inventory, and it will tell you if the router has any DSPs or any line cards, T1s, so on and so forth. But for a switch, which is what we're on now, that's all you get, at least in user exec mode. So now, as an example, I'm going to enter a command that's not valid. For example, I will type show run and hit enter. And it actually tells us invalid input detected at caret marker, and it shows you where in your command line you typed an incorrect command. In this case, it doesn't recognize run as a valid argument for the show command because, again, we're in user exec mode, so it's pointing at this run saying you can't enter run as an argument for the show command. Now, this question mark help works even if there's more than one argument required. For example, if we do show VTP and hit question mark, we see that the valid commands for this point in the command line is counters or status. So if we do show VTP status and hit question mark, it says there's nothing else you can do. You can pipe it out to a file or pipe it out to another command, or you can hit the carriage return and just run the command. In this case, we do show VTP status. We're not running VTP because this guy has a generic vanilla out-of-the-box configuration. So you'll notice that one of the options for the show VTP status was the output modifiers. The output modifiers can be your best friend, especially if you are doing a show run on a router or a switch where the running configuration is just impossibly long and you only want to pull out certain parts of the configuration. So we'll do show VTP status, and we'll do the pipe, which is shift and the key over the enter key that's above the backslash. If we do that and we hit question mark, we get several options for the redirection commands. Now these vary based upon the platform and upon the version of the iOS that you're running on the device. For example, some of the routers that you'll see as we progress through this course will actually include a section command. So you can say pull out just the EIGRP section or just the RIP section and show me just those configuration commands. This switch does not support the section command, but we can do begin or count, exclude, format, or include. So for example, let's say we wanted to include lines that included the word mode. So we do include, and then we type mode, and you'll notice the only lines that get returned are these three here, the operating mode, the pruning mode, and the VTP v2 mode. Those three lines are the only ones that are returned. So if you were running, for example, a show interface status, and we piped that through, and we only want to include lines that have the word down in them. Obviously, there's none that include the word down. Okay, so it's not connect in this particular iOS. So if we do show interface status, we do include not connect. I may have just hit a bug in this particular version of the iOS. At any rate, it should pull out any lines that have the not connect word in it. So we'll pick up with our basic command line interaction in the next video. So we are continuing along with our discussion of the basic Cisco command line interface. And the more astute among you may have noticed that I didn't actually enter all of the commands up here. I didn't do show interface status pipe include not connect. Which, by the way, over the course of the break, I actually opened up another console window and I figured out the reason that didn't work is that the show interface stat is different than show interface status. And that's what the command is actually supposed to do. In this case, it looks exactly the same as the previous command because there's only two interfaces on the switch that's actually connected to something else. But all of that aside, you'll notice that I didn't actually spell out the word show, interface, and include. And that is another feature of the Cisco iOS, and it's kind of a lifesaver in that Cisco only requires you to enter enough of the command so that it is not ambiguous. For example, if we go back here to the help, we notice that, for example, there are two commands that start with DIS, disable and disconnect. So if we were just to try to enter DIS and hit the question mark, it would actually tell us ambiguous command DIS. It doesn't know if we mean disable or disconnect. In this case, if we were to go back and do DISA, it would know, oh, you want to disable certain commands from certain privilege levels. And we'll get into how exactly to do that elsewhere in the course when we talk about securing a switch, or we'll at least touch on the subject. We won't actually delve too deeply into it. But this just goes to show you that Cisco's pretty intelligent when it comes to these types of things. Another lifesaver is tab completion. For example, if I were just to do that same DIS and hit tab, you notice that right now it doesn't actually give me anything other than the same command I've been typing in. But if I were to do DISA and hit tab, then it fills out the rest of the word for me. Now again, that's just an extension of the same logic that figures out what commands you mean after you've entered enough characters. But it's also a good sanity check so that you know what command you're actually entering. And even though I don't have to enter in the entire word disable, I always hit tab, or most always hit tab, just so I know, hey, it's actually disabling something and not disconnecting something. Going back to the ambiguity question, if I were to do DIS and hit question mark, it would show me that the only two commands to start with DIS are disable and disconnect. Now that's different than if I enter space and question mark. This first command is saying what starts with DIS. The second is saying my first command is DIS. What other arguments can I specify for the dis command? In this case, it's saying, hey, that's too ambiguous. I don't know what it is. In this case, it's saying you can either disable or disconnect. So enough mucking around here in user exec mode. Go into privileged exec mode. Privileged exec is its technical name. Most anyone that deals with Cisco switches will call it enable mode. And quite simply, that's because that's the command you enter to get to privileged exec mode. You do enable. You'll notice that we can enable to a certain level if we want to do testing, or we can just hit enable, and you'll notice that now our prompt has changed to have a pound sign or a hash mark at the end of it. And that indicates that we have more commands available to us. In this case, since we enabled with no other commands or no other arguments after it, we are automatically at enable level 15. In this case, if we hit the question mark, you'll notice there's a lot more commands available to us because we are now the switch administrator. There's 4 pages of commands or 3.5 pages of commands. And the most common command, show run, we can actually show the running configuration of the switch now, go all the way down through all of these. Like I said, it's purely generic, so there's really nothing in there to write home about. Also, now that we are in privileged exec mode, we can do show run, and we can look at some of the redirection commands available to us. And you'll notice that now we can actually take the output of commands and send it out to a URL. In this case, an FTP is the most common, although you can do HTTP with certain configurations. You can just flat out redirect it to that URL and overwrite any file that happens to be there. You can copy it to a URL. And these URLs can be anything that supports file operations. Again, a TFTP or an FTP server are the most common, but you can also write the configuration out to another file on the flash. For example, if we do R for redirect, you'll notice that there are all of the URLs we can send it to: flash, FTP, NVRAM. We can put it out to an SCP or a TFTP server. In this case, we could do flash and do run2.txt. And that redirects the running config out to this run2.txt. If you had to send it into Cisco support or you needed to send it to another engineer for review. And now you can look on the flash and you can see there's a run2.txt out there along with the actual running configuration, which there is no running configuration because this is generic and out of the box. Again, you can also do a T, which says T it out to run2, or I have to specify flash actually, flash run2.txt. And I'm going to overwrite this file. The difference between redirect and T is that T actually sends it out to the display as well. So if you want to be certain what you send out to that file is the correct information, you can T it out to both the display and the file. And that's pretty much the basics of interacting with the command line interface. There are some command line editing tools or editing shortcuts that allow you to jump to the beginning of the line or jump to the end of the line or so on and so forth. And while we won't go over all of them here, we will go over some of the more common ones that you'll use every day. The first is just like the Windows command prompt. If you hit up arrow, you can get the last command or the last few commands that were run inside this console session. There's all the commands that I ran as part of this particular video. You can also jump the cursor to the beginning of the line by hitting Control A. That jumps the cursor to the beginning of the line. Control E jumps it to the end of the command line. And of course you can do Escape B to go back one word, or Escape F to do forward one word. Now I've made a handy-dandy chart of all of the command line editing keys, and it's included as part of the work files for this course. You can go over them in your spare time. You really won't be tested on them, but they are good to know, especially if you're having to issue a really long command on the command line or a really long configuration directive and you mess up one little part of it. You misspell a word and you don't want to have to retype in the entire command or hit the back arrow half a dozen times to get back to exactly where you messed up. You can use these command line editing tools to get to exactly the part of the command line you're after. And that's pretty much it. That covers our basic introduction to the Cisco command line interface. So we're going to continue with our discussion of switch configuration, and we're going to talk about the initial configuration dialog. Now, the initial configuration dialog is what comes up on a router or switch whenever it is booted and does not have a configuration in the flash. In our case, we're back here on our 2960, and I've reloaded it. You'll recall that we didn't put a configuration on it earlier. And so after it reloads and it goes through all of its self-test, if we scroll up through the scroll back buffer here, you can see where it reloaded it and it loaded the iOS, gave us the copyright information, checked the file system, checked all the hardware, gave us the serial number and the model number, so on and so forth. And it finally comes down to this: would you like to enter the initial configuration dialog? We're just going to step through this dialog, and you'll see some of the items that you can configure here with this dialog. If you hit no, then it just exits directly to the user exec prompt. And we've already seen that a little bit. So we'll just enter yes here. We'll hit Y for yes. And you'll notice that we still have the question mark available to us, and we can also see what the default value is because it's in brackets. So first it prompts us for basic management setup. Basic management setup pretty much configures an IP address on the VLAN 1 interface, and every switch port by default is in the VLAN 1 VLAN. And so that means if this switch is connected to your network on any of its physical ports, then you should be able to get to this guy using this IP address, assuming you can actually route to that address. So yes, we're going to go through basic management setup. The first thing we want to do is configure the global parameters. In this case, we want to enter a host name. It defaults to switch because that's its default name. In this case, we'll name it C2960_lab. And hit enter. It now asks for the enable secret. You'll recall when we talked about the command line interface in the previous videos. When we went into enable mode, we typed EN for enable and hit enter. That it just went directly into enable mode, and that is because we did not have an enable secret set. It's always a good idea to set an enable secret. Otherwise, anyone that guesses a username and password for your switch will have full configuration access into your switch. That enable secret is just one more level of security. In this case, we'll make the enable secret enable. You'll notice that it does echo it out to the screen so that you can actually see what you're entering. So our enable secret is enable. And it also prompts you for the enable password. The real difference between the enable secret and the enable password is that some of the older iOS images use the enable password. Essentially, it's just a different method of encrypting the password. The enable password uses a reversible encryption. The enable secret does not. In this case, we'll make the enable password and the enable secret the same thing. That's always a good idea just from a sanity standpoint. So we'll do enable for that guy as well. And actually in this version, it makes you specify a different enable password. So we'll do enable 1. Next, we're prompted for the virtual terminal password. The VTY password is the telnet password or the SSH password. This is a password that's required before you can even get user exec privileges on the switch. Again, it's always a good idea to set this. And in fact, if you don't set a VTY password, you cannot actually telnet into the switch. It just tells you quite literally when you connect, telnet password required but none set. In this case, we'll make our terminal password, the word password, super secret. And next we're prompted if we want to configure SNMP network management. We won't go into SNMP network management in this video because it's a lot of settings that we don't really need to get into quite yet. Obviously the default is no. If you choose yes, then you're prompted for the read and write community strings and perhaps an access list, depending upon the version of the iOS you're using. In this case, we'll hit enter and say no. Here's our current interface summary. All 48 of our ports and our 4 gigabit ports. Now you'll notice that it asks you the interface name to be connected to the management network from the above summary. Now you can specify a single interface, like Fast Ethernet 040 for example, and it will assign the management address to Fast Ethernet 040 and only that one interface. While this may work well in some situations, generally it's a good idea to assign the management connection to VLAN 1. This way, any interface that's in VLAN 1, and again, by default, it is every interface on the switch, can be used to connect to it for management access. In this case, we'll tell it VLAN 1, configuring interface VLAN 1, configure IP on this interface. The default is no. We'll tell it yes because we actually do want to configure IP on this guy. The IP address for this interface, we'll give it 10.10.10.1. Subnet mask, it defaults to the Class A subnet mask since 10. Is a Class A network. In this case, we'll make it a Class C network. And again, we're asked if we want to enable as a cluster command switch. And again, cluster commands are actually a little outside the scope of the CCENT, so we're just going to say no at this point. And then it tells us what configuration file has been created, and it gives us a chance to look through this file for any obvious errors. In this case, interface VLAN 1 is not shut down. There's its IP address. There's our enable secret and our enable password. We go all the way down through here. It's not configured anything interface specific. And now we're given the options. The last time we can back out of this, we can tell it to go to the iOS command prompt without saving the configuration. This way, if you wanted to specify some interface-specific configurations, you could do so. You could just throw out all of your changes or save the config to NVRAM and exit. In this case, we'll choose the default, which is number 2. Builds the configuration and dumps us right out to user exec. Now, if we enable, and our enable password is enable, and we do a directory on the flash, we can actually see that our configuration is there. There's our config.txt. And no, it's not really 13 minutes after midnight on March 1st, 1993. That's just the default time for the switch since we have not specified a time server. But that covers the initial configuration dialog, and that brings us to the end of this video. In this video, we're going to discuss advanced switch configuration. Now, you've seen in our previous videos where we've discussed the initial switch configuration that we ended up with a good basic running configuration. However, like anything to do with networking or computers in general, that basic configuration doesn't serve all of our needs until it's fully customized. And we won't go into all of the various configuration options necessary to get the switch up and running, but we will touch on some of the advanced monitoring commands and advanced configuration commands that you might use on your Cisco switch. Now, we are connected to our 2960 lab switch that we've been working with throughout the course of the video here. And you'll notice that we're in enable mode, or privileged exec mode, as it's actually technically known. So obviously some of the commands we've looked at before are under the show commands. And since we are in exec mode, in privileged exec mode I should say, we have many more commands available to us than we did in user exec mode. The one that most everyone will use first off is show run, to show the running configuration. And if you've just gone through the initial configuration video, then this configuration is exactly what that configuration wizard came up with. It's not been changed. I've not done anything in the background to make this work better or worse. It is what it is here. So if you're looking at a switch and you've verified the running configuration, then one of the other things you can do is do a show ver to show the version of the software that's running on the switch. In this case, it is C2960 LAN Lite version 12.2.50. It tells you how long the switch has been up. It's been up for just over a day, just over 24 hours. It tells you what the system image file is. In this case, it booted off the flash, and there's the image name that it booted off of. You then get further down in the version and it tells you that this is a 48-port switch with 64K of memory. It's got one VLAN interface. Because this is a layer 2 switch, we can have multiple virtual Ethernet interfaces or VLAN interfaces, but only one can be active at any given time. It tells us we have 48 fast Ethernet interfaces, 4 gigabit Ethernet interfaces. Gives us the MAC address, the serial numbers, and if this switch was a stackable switch like a 3750, it would actually tell us how many switches are in the stack, their model numbers, the software versions, and the software images for each of the switches in the stack. So now that we've shown you 2 of the basic show commands that you'll use on nearly every device you connect to, let's actually start configuring some of the settings on the switch. Now, a lot of these settings were configured using the initial setup wizard, but we're actually going to go change some of those commands, just so you can see what it's like to do some of the more advanced configuration options. We will also set a login banner to kind of warn off people from trying to hack into our super secure switch here with its super secure passwords. So the first thing we'll do is we'll enter configuration mode. In this case, we'll do configure. And we have several options we can configure from network or terminal, or we can replace the running config or so on and so forth. In this case, we're going to config from the terminal. We only have to enter the T because it's the only option for configuration that begins with a T. So now we're in configuration mode. So the first thing we'll do is we'll change out our telnet password. If you'll recall from our initial configuration, we have the extremely secure telnet password of password. So let's go in and change that. Now you'll notice that these are the VTY lines. These are the virtual telnet lines. We have 0 through 4 and 5 through 15. And the reason they're broken out this way is that older iOS versions only supported 5 telnet connections at a time. Later versions support up to 16 simultaneous telnet connections. Why you'd need 16 people telnetted into a switch at any given time, I have no idea, but I suppose that the need was there, or else Cisco would not have put the option into the iOS. So the reason it's broken out like this, and it's broken out like this by the iOS, you'll notice that we are not going to enter the two sections. It'll break it out for us. It's so that if you were to copy this configuration and paste it into another switch that did not support the extended VTY lines, then your first 5 would be set properly, and you would just get an error when you put in line VTY 515. It would come back and say, hey, that's not a valid VTY line. So let's go back down here to our configuration, and we will do line VTY 015. So we're going to configure the login and password for all 16 VTY lines. Now, in theory, you could configure a different password for each of the 16 VTY lines individually, but why would you want to do that? Because you don't really ever know which one you're going to connect to. So now we're configuring the line. If we hit question mark on here, we see we have all kinds of options for configuring these VTY lines. Now, the one we're interested in down here is the password. We're going to set a password for all 16 VTY lines. We'll pick that up in the next video. So we're going to carry on with our configuration of passwords here on our VTY lines. We're going to enter the password command, and we're going to hit question mark just to see what options are available to us. Now, by default, if we just enter a password, it's going to assume that this is an unencrypted password. You also have an option to use a hidden password or an encrypted password, and that's useful if you have an outside company or a lower level engineer or technician that you need to configure your switches. You need to have them take them out of the box and put the configuration on the switch before they're sent out to the field. But you may not necessarily want that third party or that lower level technician knowing all of your telnet and VTY and console line passwords. So you can specify that the passwords are encrypted, which we'll show you how to do that elsewhere in the course when we talk about securing the switch. And that way, as they paste this configuration into the switch, or as they TFTP it into the switch, they can't just look at the config and figure out what your passwords are. In this case, since I'm not nearly good enough to come up with an encrypted password that's actually anything logical, I'm just going to enter the password, password1. Super secure there, and we'll exit this. And if we show the running config and go all the way to the bottom, you'll notice that now our VTY04 and VTY515 passwords have both been set to the same thing. Now, the last item we're going to talk about in our advanced switch configuration is banners. Now, there are several different banners that you can set on the Cisco switch, and we'll talk about all of them briefly here in just a moment. The one we're going to set is the login banner. This is the banner that is presented to incoming connections before any username or password prompts are asked for from the connecting user. So we go into config mode to do this. So do config T, and we'll type banner and hit question mark. And there are several different banners, as we mentioned. We can set just any type of banner we want here without specifying one of the types of banners, and by default it's going to set the message of the day banner. You have the exec banner, which is the banner you see after you log in once the user exec mode has started. You have the incoming banner, which is shown on your terminal lines before you're even prompted for usernames and passwords. So you could, in theory, set an incoming banner for telnet that basically says, we don't allow telnet, go away. And since there is no exec process enabled for that VTY line, it would just display that banner and then disconnect. In this case, we're going to set the login banner, and the login banner is what's shown, again, before any username or password prompts. We'll do banner, login, we hit question mark, and now we're going to enter our banner text. Now, it could be just a simple one-line banner text, hello world or whatever, but we're going to enter a multi-line banner. And when you do this, you have to come up with a delimiter, and that delimiter can't be anywhere in your banner text, so it's best to set it to like a hash sign. Or Control-C. I've seen some people use Control-C as the banner delimiter. In our case, I've got a cute little graphic, so I'm just going to use the hash mark here. And now it says enter text message in with the character pound. Now, there's a little bit of an idiosyncrasy with that, which we'll talk about here in a second. So I've gone out to a website and I've gotten an ASCII art of the words lab switch, and that's what I'm going to put in for our login banner. So I'll copy that, go in here, and paste it there. And the way this banner works, if you were done with this and you think, oh, well, I'm done, I'm just going to enter the pound key here, and you enter pound, well, it doesn't exit the banner mode. Basically, the way this has to work, you have to have a character and then the delimiter. The delimiter cannot be the first character of any line. I consider it a bug. I'm sure Cisco probably considers it a feature. In this case, we do that, we're bumped back to the config mode, So I'll hit Control Z and I'll write the config, and then we'll exit. We hit return to get started. But where's our banner? We set a login banner. Well, you'll notice that we're not ever prompted for a password here on the console. And this leads to the other password we were going to set. We're going to enable password authentication for the console port. In this case, I will go ahead and go into enable mode. We'll go into config T. In this case, we're going to use line console 0 because that is the console line. So now if we type login, that enables login, and actually we'll hit question mark just so you can see what the help is for it. But you see login enables password checking. So we'll do login, and we could say local to say I only want to use a local database, or if you have a AAA or a radius authentication server, you can use that here. In this case, we don't have that on our network, so we'll do login. It says login is disabled until a password is set, so we have to set a password before it will ask for a password. In this case, we'll do password, and I'll do Cisco1 as the password. So exit that, write the config, and now let's see if we get that login banner. So let's quit, press return. There's our lab switch banner, and the reason we get it now is because we have login enabled for this. Now we're being asked for our password, so we'll do Cisco1, and now we're in user exec mode just as we expected. So now you know some of the basic configuration settings to enable login and password checking on the switch. You've hopefully gotten comfortable with going into and out of configuration mode and writing your config, and hopefully that'll be a habit that's ingrained upon you, is that you write your config frequently so that you don't run the risk of losing all of your hard work after a power failure. And that concludes our discussion of advanced configuration. In this video, we're going to discuss switch security. And obviously there are entire courses and entire books that are written on Cisco switch security. For the IC&D1 exam for the CCNA, all you have to worry about for switch security is Telnet versus SSH. Now, if you've dealt with networks for any period of time, you know what Telnet is. It's that wonderful protocol that lets you connect to devices remotely so you don't have to run around your network with a console cable plugging into all of your routers and switches or firewalls or refrigerators or whatever is out there that supports networking. However, Telnet is quite insecure, as we'll demonstrate here with our packet capture. We love Wireshark in this business, and so let's look at a Telnet login to a switch. And I've included this Telnet login as well as the SSH login file that we're going to look at next as part of the work files for this course. So I'll go ahead and expand the Telnet window down here and shrink this down so you can see everything. This is a Telnet session between a workstation and a switch in my lab network. So as you can see, I initiate the Telnet connection, and we get the login banner, have a wonderful day, and I'm asked for the username. In this case, I will send my information, FRED, so that's the username. I hit enter. It asks me for the password, and since it doesn't echo the password back, I only get one character in the Telnet traffic for the password. So there's FRED. And there's my lab switch 1 prompt coming back from the switch, so we can already know that our Telnet password is Fred. Obviously, that's a very simple password, but it could be any complex password in the world. It's out there on plain text on the network. So now we're going to enable. There's our enable password, CISCO, enter. There's the enable prompt. We're going to show run. And there's the running configuration of the switch just spit out on the network in plain text for anybody to happen to grab off. Obviously, Telnet will do in a pinch, but it is not secure by any stretch of the imagination. On the other hand, let's go and look at SSH. Now, this is the same switch. You can see it's the same IP addresses, and we'll shrink this down here and open up the SSH protocol window. And you can see that we connect here. And once we negotiate the keys and whatnot, you can see that all the data after that is encrypted. You could, in theory, decrypt that, but by the time you decrypted it, the data would be useless because it would be several years old by the time you decrypted it, if you set SSH up correctly. So as you can see, SSH is pretty much required if you're going to keep your network traffic, your administrative traffic to your switches secure. So how do we do that? There are a few steps to enable SSH on a switch, and we'll go through all of them. First off, we have to set a username and a password that's permitted to log in on the switch. So we'll go back here to our handy dandy lab switch. We're already enabled, so we'll go into config T. And the first thing we have to do is set up a username, because obviously we were not prompted for a username when we telnetted in, and SSH requires a username and password. It's just integral to the protocol. You can't log in without one, without a username at least. So let's use the username command, user, and hit question mark. We are prompted for the username. In this case, I'll keep it consistent with my test switch, and I'll give the user as Fred. We have several subcommands after we specify the username. The two we're going to be using is privilege and password. So the first thing I'm going to do is say privilege, hit question mark, and we're given a privilege level between 0 and 15. 0 is the most restrictive. It's just the basic login prompt. 15 is enable mode. So you have granular control over how much privilege each user has on your network device. In this case, we're going to say Fred is an administrator, so we'll give him privilege 15. After that, we can set the password, so we'll do password. And I'm going to specify password 0, even though it defaults to unencrypted, just like with the telnet and console passwords. In this case, we will keep it consistent, keep his password as Fred. So now most people say, well, I've set a username and password. I should just be able to log in using that username and password. Well, let's test that theory. So we'll connect to this switch via telnet. So once we connect, we're just prompted for the password. Why weren't we asked for the username? Well, we'll enter Fred as the password. Obviously, Fred's not the password. The actual password is password 1, I believe. Yes, password 1 for telnet. And we're dumped into user exec mode. So we'll go ahead and exit from this guy. So there is obviously another step to be done with the VTY lines. So let's go back into config T. We'll do line VTY 015. And the magic sauce, if you will, in this is in the login command. You remember we did login and question mark. We have the option for a local password checking. And again, if we had a radius server configured with the AAA server commands, then you'd have more commands than local in here. In this case, we'll do login local, and we'll write the config just to be on the safe side. So now we should get prompted for our username and password. So we hit connect. Now we're prompted for our username, FRED, password, FRED. And since he's a privileged 15 user, he's dropped right into the privileged exec mode. No need to actually enable to get access. So that's well and good. Does SSH work at this point? Well, we have an SSH key already, just by virtue of running through the initial setup. However, if you had to set it up on a switch that was already running, you go into config T, and the actual command is crypto key generate, and we're going to generate an RSA key. I'm sorry, we have to specify a domain first. I can't believe I forgot that. So we'll do IP domain name, and we'll do test.local. Now we'll do crypto key generate RSA. How many bits in the modulus? We'll just leave it as the default as 512. Again, that's good enough. Some administrators specify 1024, 768, or 2048. We'll just leave it as the default. So now it's generating 512-bit RSA keys, and so now we can actually do IPSSH version 2 to specify we only want to use version 2 and not the older, more insecure version 1 SSH protocol. And so now let's see if SSH works. So let's connect here with 2960 SSH. We'll give the username of Fred, the password of Fred, and there we are. We're now connected with SSH. However, we're still connected with telnet. Let's go out here and write the config, again, just to be on the safe side. And if we exit telnet, we should still actually be able to connect with telnet. So let's do 2960 telnet. So we still accept telnet connections to our switch. How do we turn that off? Well, again, it's part of the line configuration here. And it's a command we haven't used so far, so we'll go into config T line VTY 015, and it's the transport command. So transport input, define which protocols to use when connecting to the terminal server being this switch, and we have the options for all, none, SSH, or telnet. In this case, we're only going to do transport input SSH, and go out and write the config. So now let's try to connect via telnet, and let's see what happens. So we do 2960 telnet, The remote system refused the connection because we are not permitting telnet connections through this guy. However, we can still connect with SSH just as a test. We'll do Fred, and there we are. So now we have secured our switch, at least as far as ICND1 is concerned. And that concludes our discussion of switch security. In this video, we're going to discuss port security. And again, like most things with the CCNA, we'll only scratch the surface of all the various port security settings that a modern Cisco switch offers. However, this video serves as a good introduction to port security. It introduces you to the port security commands and shows you a basic way of locking down the ports on your Cisco switch. So let's get started. Here we are on our switch. We are in privileged exec mode. And of course, like with all other configuration commands, we have to enter configuration mode. So we'll do config T, and then we're going to pick the interface that we're going to configure port security on. Now, if you're going to configure multiple interfaces with the same commands, you can actually use the interface range command. So you could do interface range fast Ethernet 0/1 to 48 if you wanted to. And if you do that, you'll notice that it switches to config IF range. And so any commands you type will apply to all of the interfaces immediately upon typing them. So if you're connected via telnet and you type the shutdown command, well, you're going to be finding that switch and plugging it in with a console cable. When it comes to port level or interface level configuration commands, it's generally best to pick a small range of ports, say 1 port or 5 ports or 10 ports. Test the configuration on that, and then if that works and you're not kicked out of the switch, then let's move on and configure all the rest of the ports with it. In this case, we'll exit from interface range mode and we'll just do interface fast Ethernet 0/5. Now, the first thing we have to do before we can configure port security is set the switch port mode to access. And at this point in the certification exams, you don't really know the difference between access mode and trunk mode on a switch. You will cover that in the ICND2 exam if you continue on and get your CCNA. However, for the purposes of the exam, which is what we're teaching to here, the command you need to know is switch port mode access. Once you do that, you can use the switch port command. And there's a subset of the switch port command that is, oddly enough, named port security. So you'll do switch port security, and you'll notice that there are 4 commands you can use underneath switch port security. Now, before you can use any of those commands, you have to actually enable port security just by hitting enter. Now you can configure the other aspects of port security as listed here in the help commands. So the first command we'll look at is that MAC address command. You see aging up there at the top, and we'll come back to aging once we talk about MAC address and maximum, because it'll make a little more sense then. So we do switch port security MAC address and hit enter. And first off, we're presented with the option that we can configure a 48-bit MAC address. Now, when you configure a secure MAC address on a switch port, which is what you're doing with this command here, the switch port security MAC address command, what you're telling the switch is, I only want you to accept traffic from this MAC address on this port. And there's another command you have to enter to actually lock that down. But if you enter switch port security MAC address and you enter a MAC address, what you're doing is telling the switch, if you see this MAC address on any other port, just don't accept any traffic from it. Now, if you don't happen to know the MAC address, you can issue the command sticky, and it will learn the MAC addresses and put them in the running configuration for you as it learns them. I will be perfectly honest, I have only seen this used 1 time in all of the years I've been doing computer networking, and that was a core switch in a very small network where all of the servers and internet connection and so on connected to that core switch. On edge switches, it can get to be an administrative nightmare if you have to go in and change MAC addresses every time someone's computer moves or every time someone switches out their phone or their network card. It can be a pain, so most installations don't use switch port security MAC address. What does get used quite often is the switch port security maximum. And what this will allow you to do is specify the maximum number of addresses allowed on a switch port. Now, if you configure, for example, 5 MAC addresses using the switch port security MAC address command, and then you set the maximum to 8 or 9, let's go with 9 just because it's the highest number I said. then that will essentially allow you to connect up to 4 more devices to that switch port other than the secure MAC addresses. So if you're going to use the secure MAC addresses, you need to set the maximum to the number of secure MAC addresses you've entered earlier in the configuration. Otherwise, people can just plug anything up into the switch port and circumvent all of your tightly locked down security. Where switch port security maximum is generally used in most installations is if you have an IP phone connected to that switch port, and then you have a PC that's behind that IP phone. This will allow you to say you can't plug a hub up behind that IP phone and hook up 20 machines. You can only have 2 MAC addresses on this particular port, the phone and the PC behind that phone. We'll continue on with our discussion of port security in the next video. So we're continuing on with our discussion of port security. We've just talked about the switch port security MAC address and the switch port security maximum commands. Now let's loop back and talk about that first command you see up there, which is aging. So if we do switch port security aging, you'll see that we have 3 options. We have static, which is to enable aging for configured secure addresses, and then we have the time period, which is how many minutes or seconds, and then we have the type. So we'll look at the type first off. So we'll look at type. We have 2 types of aging. We have absolute and inactivity. Now the default is absolute, meaning that after X number of minutes, clear the table and look again. You can also switch that to inactivity, which bases it upon the activity of the port. If you haven't seen any traffic from this MAC address for X number of minutes, then clear that MAC address from the secure table and allow another MAC address to take its place. Absolute is the default, and it generally works the best for the situations you'll need port security aging turned on. So we'll look back at the time, and it is the aging time in minutes between 1 and 1,440. Don't know why you'd ever want to set it as high as 1,440. Most installations use a timer of about 5 minutes or so. So now you might be asking yourself, well, I've set my secure addresses, I've set the aging type, I have set the number of secure MAC addresses allowed on a port. What happens if one of those parameters is breached? What happens if I have the maximum number of MAC addresses set to 2, someone plugs that third MAC address in, that third PC or whatever, into the switch port? What happens then? Well, that is the switch port security violation. And there are 3 types of violation modes. You have protect, restrict, and shutdown. Now, shutdown is pretty straightforward. If you violate the port security settings for this particular switch port, just shut down the entire port. Don't let any traffic through this port until you go in and re-enable it, or there are some commands you can set to automatically recover, but we don't cover those at the CCNA level. Protect and restrict have pretty much the same effect on the traffic. Both of them will just simply ignore the offending MAC addresses. For example, if you have the maximum MAC addresses set to 2 and you plug in a third device into that switch port, it'll just simply ignore traffic from that third MAC address. The key difference between protect and restrict is that protect simply ignores the traffic silently. Restrict will log it into the system log and send an SNMP trap. So if you have a piece of network management software like SolarWinds or NetVoyant or Unicenter, you can configure that software to look for the traps from your switches about port security violations and sound the alarm, send an email, whatever you want to do based upon the receipt of that trap. If you don't really care and you just want to protect it, say it's at a branch someplace and you just want to make sure that no one plugs in another hub into your network, you can just set it to protect. And generally what will happen is once people actually violate the port security settings, they'll call you and say, hey, I plugged in this hub and no one can connect. Well, you're not supposed to plug that hub in. That's why no one can connect. The system is working as designed. Now I'll close out the discussion of port security with a little note that I probably should have mentioned up when we talked about MAC address security, but I wanted to kind of separate this out because it's something that not a lot of people grasp, and I have actually seen exam questions regarding this particular statement. If you use the switch port security MAC address sticky command to tell the switch to just learn the addresses on the fly, the addresses that the switch learns are not added to the startup configuration. They're obviously added to the running configuration, and if you were to do show run after issuing this command, you would actually see them entered in the interface configuration. However, unless you write that configuration, then all those changes are lost if the switch is rebooted. So you can really think of sticky kind of as a learning mode. You tell the switch to learn the MAC addresses that are connected to it, you let it run for a day or so, Then you go and look at the running config, and if it looks good to you, then you can write that config to the startup configuration, and then the switch will remember those MAC addresses the next time it boots up. And that pretty much covers switch port security, and that concludes our discussion of switch port security. So we're going to talk about some wireless network basics in this video. And again, this is the IC&D 1 course. As a result, we're not going to get too deep into it, but we will cover what's in the exam materials. As you can probably attest, that wireless networks used to be pretty rare, but they're becoming more common in the workplace and even at home. I know I can attest just here in my home, we have 4 individuals, myself, my wife, and my 2 children. And between the 4 of us, there are probably 20 wireless devices in this home, whereas just a few years ago, before the explosion of tablets and smartphones came about, that number would have been much, much smaller. But at least in the context of a business environment, the reason wireless networks are becoming so popular is that employees require connectivity no matter what their location, whether they're in the office and just want to be able to pick up their laptop and go into a conference room and still have network connection, whether they want to take that laptop home and connect it to their home network and continue to work using VPN and remote access technologies. Or while they're traveling, let's say you have a road warrior or a worker that doesn't live near a branch location. With modern wireless technologies, they can take that laptop to any place that has a wireless connection, whether it's a Panera Bread or a Starbucks or a McDonald's even, and work just like they're in their office. And then the latest trend over the last year and a half is BYOD, or bring your own device. And this is where employees might have better computing hardware at home. They might have an iPad or an Android tablet, or they might have their own laptop that's better than what the company could provide for them. So the company just says, you know what, if you'll bring your own device, we'll cut you a check for the use of that device. Obviously, it won't cover the full amount of it, but we'll give you a check for $500 and you can go buy your own laptop and bring that in and just use that. So that way you can keep the laptop once you leave the company and so on and so forth. And without a good, secure, robust wireless infrastructure, all of these technologies just don't work, because look at most tablets. They don't have a place where you can plug an Ethernet connection into them. Wireless is just so ubiquitous now that it's hard to find a place that doesn't actually offer some sort of wireless. And when it comes down to it, at least from a business perspective, wireless networks are cheaper to deploy than wired networks. With wired networks, you have to go buy some high-speed switches, and you have to trunk those switches together, and then you have to pay to have cabling run to each of the locations where you're going to place your users. And if you have conference rooms, you have to pay to have cabling run to that conference room. And then if a user picks up and moves into a new office that may not already have cabling, you have to pay to have the cabling moved into that office. Whereas with a wireless network, you put in some wireless controllers and some wireless access points. You make sure you have enough coverage and enough bandwidth, and users can go wherever they want to go. They want to go in the conference room, fine, they can work in the conference room. If it's a really nice day outside, they can pick their laptop up and go outside on the front porch of the business and do their work out there. However, with all of this cost savings and all of this convenience, there does come a price, and there are some concerns surrounding wireless networks that you have to be aware of, and you have to mitigate those concerns wherever possible. And we'll discuss some of those in this video and in this section about wireless networking. The first concern, and in my opinion it's one of the biggest concerns, is the security. Unlike a wired network, wireless networks don't stop at the walls of the business. And there's a term for driving around in parking lots and seeing what wireless networks are available. It's called war driving. It harkens back to war dialing, where you had kids with modems that would just dial every number in the phone book until they happened to find a modem that they could log into. So if your wireless network is not properly secured, someone could drive out in front of your business and associate with your wireless network, and then all the goodies on your inside network, all your file servers and your printers and your workstations, they're all there for anyone to do whatever they want to with. That's a big concern, and you have to mitigate that. There are some ways of doing that. We'll talk about that when we discuss wireless security, or at least the basics of how to secure the wireless network. Along with the network security, you also have to make sure that only authorized persons access the wireless network. In other words, just because a wireless network is available in your office doesn't necessarily mean you want everybody in the office accessing it. And we won't really get into how to do radius or ePOL authentication here in the IC&D 1 course, but it is something to keep in mind. As a broad network generalist, you have to make sure that you keep this in mind, that whoever gets on the network is actually authorized to access the network. There are also several technical concerns, mainly dealing around reception. And when we discuss reception, the big three topics that always come up are reflection, scattering, and absorption. Reflection is just what it says. The wireless signals bouncing off of a wall or off of a metal door or so on and so forth. Scattering is when a wireless signal may hit a wall and the signal takes a right-hand turn because of the particular way the wall is constructed. And then you have absorption, which is I'm going through the sheetrock wall, but some of my energy is going to be absorbed by the sheetrock. And so anything that's behind that wall will not get a good reception. We also have to deal with interference. Interference can come from a myriad of sources, but the big ones you'll see in corporate settings are microwaves, cordless phones, and other wireless networks. And we'll look at the interference that other wireless networks can give you when we discuss wireless standards and concepts here in just a little bit. So let's discuss some of the common components of a wireless infrastructure. Obviously, you have to have a wireless network card. There's hardly a device out there, a portable device anyway, that doesn't have a wireless network card built into it. You also have to have a wireless access point. Again, that's what the wireless network card connects to. If you have a wireless network card, no access point, you're not going to get very far. And in a corporate environment, you're going to use a wireless controller. The wireless controller gives you the ease of access point configuration. Instead of having to go out to 15 different access points in your organization, you go into your controller and say, I want to advertise this network with this wireless key, and it configures all 15 of your access points. You can also do client device management. Some of the more advanced controllers and even some of the not so advanced controllers can do device management where you can disconnect users that happen to be using too much bandwidth or disconnect users that are acting in a malicious manner. And also, hand in hand with device management is network security. You can push out your network security policies through your wireless network and make sure that you as the network administrator or the network engineer is fully aware of everything that's going on your wireless network. And that concludes our discussion of wireless network basics. So in this video, we're going to discuss some basic wireless concepts, and we're going to discuss the various wireless LAN standards that are out there. Now, wireless networks encompass both layers 1 and 2 of the OSI model. Obviously, since there's no fiber optic or cable or anything like that to connect to your wireless network card, that it takes care of layer 1. And since wireless LANs have their own frame type, 802.11, to actually send the data across the network, that takes care of layer 2. Ethernet over wireless LAN uses CSMA-CA, that stands for Carrier Sense Multiple Access Collision Avoidance. Now that differs from the standard CSMA-CD access method that regular Ethernet uses. Essentially, with a wireless LAN, each station has a half-duplex connection to the wireless network. In other words, the station can listen or it can transmit, but it cannot do both at the same time like a standard wired computer could. Once a workstation is associated with a wireless access point, each station is basically given the rights to transmit for a certain period of time. So it's really closer to token ring when you think about it, more so than Ethernet. But to be honest, it doesn't really use the Ethernet or the token ring frames on the wire or in the air, as it were. So we don't call it token ring, we call it Wi-Fi or wireless LAN. Now there are two basic modes of wireless networking. The first is ad hoc wireless networking, and it is referred to as IBSS, or Independent Basic Service Set. Ad hoc wireless networking is the type of network where you have, for example, two laptops that need to send data to one another. You can basically configure both laptops with the same SSID or security set identifier and tell them to connect to one another, and they'll connect to one another. And of course at layer 3 they'll probably use those automatic private IP addresses that we talked about in IP networking, but at layers 1 and 2 you can do ad hoc networking between two endpoints. Then we have what's called infrastructure mode, and infrastructure mode is probably the type of wireless network that you're most familiar with. This is where you have a device that has a wireless network card in it, you associate with an access point, and you gain access to the network through that wireless access point. Now within the infrastructure mode of wireless networking, there's two sub-modes, if you will. First is called BSS, or Basic Service Set, and it's used when you have a single access point that doesn't talk to any other access points or communicate with a controller or anything like that. If you have a network that has multiple access points, you're using what's referred to as ESS, or Extended Service Set. And we won't get too much into both the BSS or the ESS modes, if you will, but at least for the IC&D1 you have to know what the difference is between BSS and ESS. And really, for what we're concerned about at this point, that's the difference. As a BSS is a single access point, ESS is multiple access points. So let's move on and talk about some of the wireless standards that are out there. All wireless networks are defined under the IEEE 802.11 standard. And if you've done any type of wireless networking, then you know probably all of these standards that I'm about to tell you about, but we'll cover the very basics of how these standards work and what makes them different from one another. There are 4 basic protocols in use today. The 802.A, B, G, and N, and there's a draft protocol for 802.11ac, but it's not covered on this IC&D 1 exam. In reality, I don't even think 802.11n is covered, because this exam was written about the time that 802.11n really got popular. However, you never know when they'll throw a question on there about some of the newer technologies, so I'll cover it in at least the same level of detail that I do the other 3 type of wireless protocols. So first, we're going to talk about 802.11b, and I know you might be asking, why didn't you start with 802.11a? You'll see why here in a bit when we discuss the differences between A and B. 802.11b is very similar to the original 802.11 standard, the 802.11 standard without any letters after it. 802.11b uses the 2.4 gigahertz band, but allows for higher transmission rates than the standard 802.11 standard. 802.11b allows for 3 different channels and supports data rates of 1, 2, 5.5, or 11 megabit. Next, we'll move on to 802.11a. 802.11a was actually the first amendment to the 802.11 standard. The original 802.11 standard was almost identical to 802.11b. The only difference is the original standard used data rates of 1 or 2 megabit. 802.11a uses the 5 gigahertz frequency band. Now, the 5 gigahertz frequency band is not nearly as crowded as the 2.4 gigahertz. The 2.4 gigahertz frequency band is used by baby monitors and cordless phones and microwaves and all kinds of interesting radioactive devices, I guess. 5 gigahertz is not nearly as crowded, but because it is a higher frequency, it's more susceptible to interference. It will get absorbed more easily. It can't pass through walls nearly as easily as 802.11b or any of the protocols that use the 2.4 gigahertz band. The 802.11a standard allows for 12 channels and data rates of 6, 9, 12, 18, 24, 36, 48, or 54 megabit, just like the 802.11g standard, which we'll talk about on the next slide. We'll pick up with our discussion of wireless standards in the next video. So we'll carry on with our discussion of wireless standards. We've just talked about 802.11b and 802.11a. And even though 802.11a was the first amendment to the plain 802.11 standard, it was not nearly as popular as 802.11b. And you might look at it and say, well, why isn't it as popular? Yeah, it uses a higher frequency band, and you might have to have more access points, but you've got more channels, you've got a higher data rate, and it was around first. Why isn't it more prevalent than it is? I mean, you can hardly find any type of 802.11a networking equipment out there. The reason why is that 802.11a hardware was only used by early adopters, mainly in a corporate environment where interference wasn't nearly as much of a problem. If you had interference or you had signal loss, you just threw another access point in place. This being the first iteration of the standard that was different from the 802.11 naked standard, I guess, is the best way to term it. The hardware was awfully hard to come by. Everyone was buying just a plain old 802.11 hardware. Not a lot of people were buying the A hardware because it was different, it was more expensive, and again, it didn't get as good a range, so at least for most smaller businesses that may have wanted to put in a wireless network, they'll just use the plain 802.11 standard. It's not as fast, but it gets the job done just as well. However, when 802.11b was introduced, since the hardware is pretty much the same as 802.11, the sales of 802.11b hardware pretty much took off because you had the same frequency usage and some of the same channels as 802.11, but you had a much higher data rate, again, from 1 to 2 all the way up to 11, which means that the corporate people that had already used 802.11 didn't have to buy more access points. They could basically just do a firmware upgrade to their existing access points, and they could run 802.11b. And that's why the 802.11b hardware kind of eclipsed the 802.11a hardware, even though the A hardware was around first. So anyway, that's the whole sordid story behind 802.11a versus B. Again, one's not any better than the other unless you just look at the raw data speed, but it was just a matter of getting the hardware to market quickly enough. So let's move on to what is probably the most commonly used and most popular wireless network standard out there, 802.11g. 802.11g is almost identical to 802.11b. It uses the 2.4 gigahertz band like 802.11b, but it uses the transmission scheme from 802.11a, therefore allowing you to use more of your channel bandwidth and use it more efficiently. It is fully backwards compatible with 802.11b hardware, so there was no manufacturing changes that had to be made. The same antennas, the same chipsets, everything worked with 802.11b and 802.11g. And in fact, I remember when the G hardware first came out, it was literally a firmware upgrade to the wireless access point I had in use at the time at the small company I worked for. 802.11g allows for 14 channels and allows data rates up to 54 megabits. So as you can see, you've got the best of both worlds between the 802.11b and the .11a standard. You're using the 2.4 gigahertz bands, which has a greater penetration and not as susceptible to interference, at least absorption and scattering, although you had other devices that use the 2.4 gigahertz band. However, you can get the higher data rates that the .b standard gives you. And last but not least, we'll talk about the new kid on the block, the 802.11n standard. And it's fairly new. It's been out for a couple of years, and there are already devices out there that can use the N networking standard. 802.11n has the ability to use both the 2.4 gigahertz and the 5 gigahertz frequency band, depending on which is least used for the installation where you have it. 802.11n allows for speeds up to 600 megabit, which greatly enhances its usability in a corporate network where you have to move large files around on a pretty alarming basis. 802.11n accomplishes this by basically using two antennas, where a lot of the G and the A and the B access points only had one. The 11n access points have at least two. And so you use one for transmission and one for receive, and by doing that, you'll overcome the limitations of that half-duplex connection that we mentioned way back at the beginning of all of this. Now again, the .N standard is not on the exam, and so I'm just going to cover it very briefly like we just did. But I didn't want people to watch this video and go, well, gee, this video is 7 years old. What are they talking about 802.11n for? And so just to set your mind at ease, it's not the course that's old, it's really the source material that Cisco gives us. And that concludes our discussion of wireless concepts and standards. So in this video, we're going to discuss wireless security. And obviously, when it comes down to wireless security, proper wireless security should just be a logical extension of your overall network security scheme. You need to have network security in place before you really even think about a wireless network. And too many times, people will just throw a wireless access point in their lobby or wherever and say, well, we have a wireless network, everyone can wander around. And they don't really stop to take the time to think, how am I exposing my network? How am I exposing my data to outside individuals? And many times people don't take these considerations because they just forget that wireless radio waves don't stop at the doors and the windows of your organization. And again, that seems to be a no-brainer to us as network engineers, but so many times when you point this out to someone, what happens if someone pulls up in your parking lot and just decides to start surfing your internal network? People just kind of go, oh wow, I never thought about that. And basically with wireless security, what you have to remember is you have to protect against outside threats to your data and your network, as well as just internal threats. With a proper wired network security scheme, you may have it set up so that only certain ports are activated, and certain ports are in certain VLANs, and you've got quality of service and access lists and everything applied to your wired network. And that works well enough because generally you don't have people coming into your business and plugging up to your network and doing things without being noticed at least. However, with wireless networks, we go back to our most overused and most famous scenario, which is someone pulling up in front of the business after hours or during business hours and associating with your wireless network. You may not ever see them. You may not ever recognize them unless you just happen to be alert and realize, hey, that car has been parked across the street for the last 2.5 hours. There's been a guy in there on a laptop. I wonder what he's doing. Most businesses, however, don't really even consider that. So what are some of the outside threats that you have to guard against with a wireless network? The first is war drivers, and these are people that just drive around with a laptop and a wireless network card looking for open wireless networks. And most of the time, these war drivers are really just looking for free internet, but every so often you will have someone who war drives around looking for closed networks just to see what's out there. And I'll readily admit I've actually done some war driving just to see what's out there. Not that I would do anything malicious against any of the networks that I did find, whether or not they were open or closed, but just as an example, I have a small recording booth in my house that I record this in. So I'm actually sitting out in my garage recording this video right now here in the middle of a residential subdivision. And I loaded up a copy of Insider and plugged a USB wireless network card into my computer here, and I've got it cranked up. It's been running here for just a little bit. And sitting right here in my house, I can see 14, 15 different wireless networks. Everything from Apple, Netgear, Linksys. Some of these are mine. 4 of them are mine. But most of them are ones from my neighbors as well. And this particular piece of software gives you not only the list of SSIDs that it sees, but it sees what channels are available so that you can pick a channel that's not really being used by many of your neighbors so that you get a better throughput. Obviously, no one around me has 802.11n. It's all 802.11g because they're all using the 2.4 gigahertz channels. But this just gives you an example of what you might see were you to load up a piece of war driving software. Now imagine if I were to take this and go into the middle of an office park and crank it up, all of the networks I would see there. And if you don't have the proper wireless security set up on those networks, well, then you're just exposing that out for anyone to see. And you move on from the fairly harmless and fairly innocuous war drivers down to full-blown hackers, and that's a term that's been misused in certain geek circles. If you use the word hacker, no, they're not a hacker, they're a cracker. A hacker is someone who hacks on code all day. They're not crackers. Crackers are people that break into networks. Whatever word is the right word to use here. The end result of all this is there is a group of people out there that will use poorly secured or unsecured wireless access points as an entry point into the network. Now, if they can crack your wireless security, then that's just about as good as walking into your network and plugging up into a switch, and they have full inside access to your network. They don't have to go through any firewalls or any of the intrusion defense or intrusion protection systems you might have in place for your internet connection. They're on your local network, and so that's why you have to really take wireless security seriously if you're going to do this. You also have some inside threats, and these might not necessarily be people that are just attacking your network, but they're just simply trying to make their job easier and could end up compromising the security of the network. And the biggest threat from the inside are rogue access points. And again, you'd be surprised at how often this happens on large networks and small networks. You get a user that's in your corporate office, for example, and they're like, I need to bring in 5 consultants, but we don't have 5 network jacks here. I know what I'll do. I'll just go down to Best Buy or Costco or wherever and get a wireless access point or a wireless router. I'll just plug it into this jack in the wall, and that'll give all of these consultants or all of these extra employees access wirelessly. They can use their iPads or their laptops or wherever. They can wander around the room, around the space here. Unfortunately, unless you secure that properly, you've just opened up your inside network to an unencrypted world out there. And again, they're not necessarily trying to attack the network, but they're just trying to make their jobs easier, trying to make everything just kind of work and go along, and they might inadvertently let in people that don't need to be on your network. We'll carry on with our discussion of wireless security in the next video. So we're continuing on with our discussion of wireless security, and we've talked about all the bad, evil people out there that want to crack into our network and steal all of our corporate data or non-corporate data or any data at all, really. So how can we protect against those people? Well, wireless LAN security has 2 basic components. We're talking about authentication and encryption. Authentication ensures that you are talking to the access point that you think you're talking to, and that the access point is actually talking to your client. So that hopefully, unless that authentication key gets out, you're not susceptible to a man-in-the-middle attack, where you're associating with someone's computer or a rogue access point, and they're intercepting all of the data before passing it along to the actual access point. Encryption guards against that eventuality by encrypting the data or scrambling it as it goes over the air, so that even if the authentication is broken, the encryption is still there so that the data can't easily be gotten at. The wireless security standards discussed in this slide deck and in this video cover both authentication and encryption. Now, these standards come from the IEEE and the Wi-Fi Alliance, and some vendors obviously have proprietary solutions. Cisco had a proprietary solution between WEP and WPA. And around the same time, I remember seeing proprietary security solutions from Dell and Motorola. However, for the purposes of this video, we'll only be discussing standards that are standard and not proprietary. So we'll start off with the open network, and it's not really a wireless security standard, but we do need to cover it just because there are a few of these out there. Open network basically has no security settings and no encryption. And you might think to yourself, well, who in the world would use an open network with no security and no encryption? Well, you use them for public Wi-Fi access, like at hotels and coffee shops and restaurants and so on and so forth. Obviously, in situations like that, you don't want to have to worry about distributing a security key or setting up logins for each user that happens to walk into your restaurant. You just open up the network, you insulate it from your production network if you have a production network, and just let the users go out and do whatever they want to for the most part. In an open network, the SSID is broadcast and is available for anyone to connect to. There's no filtering or authentication or anything like that going on the security side. However, the downside of this is with the right tools, a malicious user can capture all of your network traffic and examine the contents. And it's for this reason that any serious security expert will tell you don't log into websites using non-HTTPS or non-encrypted means when you're on a public wireless network. And again, if you'll go back to some of the Wireshark captures we've done, Telnet is not encrypted, FTP is not encrypted, plain HTTP is not encrypted, so any of that could be grabbed right off the wire off of an open network. So doing that is generally a bad idea unless you're using some type of encryption, some type of VPN, so on and so forth. Beyond having the right tools to capture the traffic, a malicious user could just set up a rogue access point, trick everybody into associating with that access point, and then they see all the data as it flows across the wireless network, and they can mine that for interesting usernames and passwords and so on and so forth. So unless you really want everyone to come in and use your network, you don't need to set up an open security network. So next we'll talk about the wired equivalent privacy, or the WEP protocol. In modern times, this is just marginally better than an open wireless network. It was first introduced by the IEEE in 1999. WEP uses a 40-bit encryption key with a 24-bit initialization vector. With WEP, the encryption keys are statically defined between the access point and the client. So you set up an access point with a certain encryption key, you go to your client, you give that same key to the client, and that's what they use to encrypt the data with. With WEP, these encryption keys don't change like they do with some of the more modern security protocols. And so therefore, once you figure out what that encryption key is, you can decrypt anything going across the wireless network. And in fact, in 2001, the WEP protocol was compromised, and now you can crack it with a standard PC and a wireless network card using off-the-shelf software scripts. In fact, I remember seeing an app for my Android smartphone that could crack WEP networks. So essentially, WEP is just about as good as open because anyone with just a few clicks can crack into your network and get at all the goodies there. Now, there are some ways to enhance the security, or some ways that some people think they can enhance the security of WEP networks. The first is SSID cloaking. You basically hide the SSID so the user, in effect, has to know what the name of the network is before they can connect to it. Again, this works for the most part. However, it is possible to actually send out a wireless probe packet that requires every access point that receives it to broadcast the SSID or to reply back with the SSID, not necessarily broadcast it. And so SSID cloaking is basically circumvented at that point. The next is by using MAC filtering. You write down all of the MAC addresses of all of the wireless devices that need to connect to your wireless network, and you only allow those workstations or devices on your wireless network. And again, that's easily circumvented just by simply figuring out what one of the allowed MAC addresses is and changing your workstation's MAC to match one of those allowed MAC addresses. So, as you can see, these are some ways that people say they can enhance the security of WEP networks, but when it comes down to it, there really is no security on WEP networks. Even if you hide the SSID and you filter out the other MAC addresses, it's easily circumventable all the way around. So we'll carry on with our discussion of wireless security and wrap it up in the next video. So we're going to conclude our discussion of wireless security in this video. We've talked about the need for wireless security. We've talked about open networks and wired equivalent privacy networks, or WEP networks, which are pretty much the same thing nowadays. So let's carry on and continue with some real network security. Next, we're going to talk about Wi-Fi Protected Access, or WPA. WPA was released by the Wi-Fi Alliance in 2003 as a response to WEP being compromised. The WPA protocol came from the work being done on 802.11i, which is more widely known as the WPA2 protocol, and we'll talk about that on the next slide. You can use either the pre-shared keys like you do with web security, or you can use an 802.1x authentication server so that you don't have to go around to all of your corporate users and set up the pre-shared key on all of their workstations and iPads and tablets and so on and so forth. Now, whichever method you use for authentication, as far as encryption goes, WPA uses TKIP, or the Temporal Key Integrity Protocol, to ensure the security of these network keys. TKIP also rotates out the encrypted keys so that even if you capture one of the keys using a wireless sniffer, it's going to change after a while, and so you have to start this whole cracking process over again. Unfortunately, nothing lasts forever. The WPA protocol has also been compromised, just like the WEP protocol, although even with modern hardware, it's very difficult to do. The first compromise that WPA had against it was against the TKIP, or the Temporal Key Integrity Protocol. And basically, two researchers found a way to predict what the TKIP keys were going to be so that they could continue to decrypt information as it flowed across the network, even though it was authenticated and encrypted. Now again, this is not as simple as cracking a web network. It's not as simple as downloading an app to your smartphone and clicking the crack button. You have to put some work into it, but it is crackable. The next way that WPA has been compromised is with a service called the WPS, or the Wi-Fi Protected Setup. Now, WPS is a way that certain routers and certain devices can be configured automatically and can help you configure the clients automatically by either pushing a button or entering a PIN, or there's a few methods of doing it. And essentially, some researchers found a way to replay the WPS setup so that they could associate any wireless device with your wireless network. So, finally, as a result of WEP being cracked, the IEEE released what's called IEEE 802.11i, which is more commonly known as WPA2. In fact, outside of technical literature, as in white papers from Cisco or Motorola, I've not seen WPA2 referred to as 802.11i in quite a long time. If you go and you pick up a router off the shelf at Fry's or Best Buy or Walmart, you're going to see WPA2 encryption, and it might mention 802.11i, but most everybody recognizes WPA2. And the IEEE ratified WPA2, or 802.11i, in 2005 as the official solution to the lack of web security. Now, WPA2 is very similar to the WPA protocol, but there's enough differences in WPA2 that the protocol is not backwards compatible. You can't take a WPA2 client and connect it to a WPA network. As with WPA, you can use either the pre-shared keys or an authentication server if you happen to be using it in a corporate environment. However, instead of TKIP, since TKIP was compromised, they are using AES, or the Advanced Encryption Standard, to secure the keys. Also, it's important to keep in mind that even WPA2 is susceptible to that same WPS flaw that we discussed with WPA. But the protocol itself is secure for the time being, and if you must know, there probably is someone out there looking to crack WPA2, not necessarily for malicious purposes, but as part of research to determine how vulnerable is this protocol. Because, if this group of researchers can do it, then this group of hackers over here in whatever nefarious hacker lair they happen to be sitting in could probably pull off the same stunt. And so you want to know that the standard that is protecting your corporate data can actually protect it well enough so that you don't have to constantly lie awake at night and wonder if all of your data is leaving out the back door of your business. That concludes our discussion of wireless security.